Hey, this is Juan Tutors, and today we are working on the June 2024 Chemistry Regents, the regions that just happened a couple of weeks ago. We are going to jump right into the questions. The most important thing on the front page, yes, there's some important things, but the most important thing is that the school is required to provide you a four-function calculator, at least a four-function calculator. So if they try to play any funny business with you and say, oh, you don't need a calculator, just do know that they are required to give you one. But with that, we're gonna just jump into question one. I do want to say this video, we are actually not just trying to give you the answers to all the problems, although that we are going to give you every answer to every problem. But we actually want to use some test taking strategies. So do understand that what the way I do the problems is going to involve test taking strategies, like for the process of elimination, how you can eliminate some answers, and other things that you can do to maximize your grade. So do understand, I'm not just going to give you the answers, although that is the end goal. And I'm going to make sure that every answer is 100% correct. I may expand on a couple of topics and give you some extra information, but because the truth is, I want to make the GOAT of all chemistry regents tutoring videos. So if you feel that this, in the end, that this video is the GOAT of all regents chemistry tutoring videos, then do let me know in the comments. Say this is the GOAT of all videos. I would really appreciate that. But for now, we're going to just jump into number one, numero uno. Which description of the atom is based on the results of the gold foil experiment in the early 1900s? This picture is a picture of the gold foil experiment. Choice one, atoms are small, dense, indivisible spheres, sorry. Okay, choice one, atoms are small, dense, indivisible spheres. Two, atoms are composed of protons, electrons, and neutrons. Three, atoms have small, dense, positively charged nuclei. Or four, atoms have electrons with wave-like properties. So one of the things that I want to say, like, however your teacher is telling you to use this video, if that's who's telling you to use the video, follow their lead. But if it's not a teacher telling you to do the video in any certain way, what I'm going to suggest is that you actually do pause the video and make a choice for a problem. Do not say, I think this is the answer, and then play. Choose, I think this is the answer, and I'm committing to that answer. And the reason I'm telling you that is that I've worked directly with students who are like, I think this is the answer. Then I tell them that it's actually a different one, and they're like, I knew it was this one. Well, did you? If you thought it was the other one, but you chose that one, actually, no, the one you chose is the one you thought it was the best to stick to. So do stick to one, because, well, the reason is that that actually forces you to start making decisions about what makes the most sense, but more importantly, fun fact, more importantly, what makes least sense. Humans have a certain capacity to understand what makes sense, yes, but we actually have a much deeper, much more thorough, much more well-developed capacity to decide what makes less sense. So try to go with what makes the least amount of sense, and cross that out. And so then you go, that leads you towards the answer that makes the most sense. So how do I go about this one? Atoms, so the choices are, atoms are, remember that Michelson Morley, no, I'm sorry, the gold foil experiment was an experiment that did tell us about the structure of the atom. So any of these answers that actually do not correspond to the actual structure of the atom have to be false. So which description of the atom is based on the results of the gold foil experiments? Atoms are dense, small, indivisible spheres? No, they're not. They are small. There is a certain amount of density to them, but they're not indivisible. Uh, and again, the gold foil experiment was a fundamental experiment that actually did tell us about the structure of the atom. Number two, the atoms are composed of protons, electrons, and neutrons. In theory, that is true. Atoms have small, dense, positively charged nuclei. That is also true. And atoms have electrons with wave-like properties. That is also true. So the other three are true statements, but which ones of these were determined by the gold foil experiment? So if you recall, the gold foil experiment literally shot alpha particles, which is actually equivalent to helium nuclei, without the electrons, shot alpha particles through gold foil. And what they found, what the gold foil experiment showed, is that almost every single alpha particle goes straight through the gold foil. meaning it doesn't even crash into any part of the gold foil. But every once in a while, the alpha particle will ricochet off of something. Extremely rarely will the particle ricochet off of something, which meant that the the gold foil, despite being made of gold atoms, is actually composed of mostly empty space. Why mostly empty space? Well, because the alpha particles, if it wasn't mostly empty space, the alpha particles would be scattered just kind of in a constant way, just all the time. But in fact, the alpha particles were able to pass through almost unimpeded most of the time. So uh, what that means, since the atom is very dense, has a very dense small part, that's what is implied by the gold foil experiment. And in fact, it's this one. The atoms have a small, dense, and positively charged nuclei. Now, why positively charged? Well, because the alpha particles are made of two protons and two neutrons. The two protons are positive, and so the deflection of the alpha particle is due to a repulsion force from the nuclei. So the nuclei therefore have to be also the same charge as the alpha particles. Okay. Now it is true that atoms are composed of protons, neutrons, and electrons, but uh, there's nothing in this gold foil experiment that can confirm the existence of neutrons. Not in this experiment, definitely not. And the other one, the atoms have electrons with wave-like properties. This, in fact, doesn't test anything about electrons at all. So that's why this one is wrong. So again, choice 3 is the only one that makes sense based on the structure of the experiment. And from there, we move on to numero dos, number 2. According to the electron cloud model, which term is defined as the most probable location of an electron in the atom? Again, the electron cloud model, which term is defined as the most probable location of the electron in an atom? Configuration, or nucleus, or orbital, or spectrum. Okay, now do remember the electron cloud model says that there's a dense uh, nucleus with protons and neutrons, a bunch of them, you know, stacked however they're stacked. There's a lot of theory going into how they're possibly stacked in the nucleus. There's even some theories that maybe that varies. But then the electron cloud model says that the electrons are like literally in clouds, and sometimes those clouds can be shaped pretty weird, on maybe in unexpected ways. Sometimes literally like dumbbells. Sometimes in other very interesting ways. We'll leave it at that. So the most probable location of electrons in an atom, configuration is, maybe there is a certain amount of configuration, but that's not the technical term for it. Okay, so they're definitely not in the nucleus. They're outside of the nucleus. There is some theory that some electron clouds do intersect the nucleus, which is weird to think about. But they're the electron clouds, best to think of them as being outside of the nucleus. Okay, so the second thing, orbital or spectrum. I could imagine why a student might be debating between these two, but if you think about what a spectrum is, if you think about what a spectrum is, when you look at light, let's say white light gets split into a series of colors, as you know, from red all the way to violet, and that is a spectrum of light of different wavelengths, and of course that spectrum is what describes all particles. They because they all have a wavelength, they appear in a spectrum. Yes, that is true, but the location of the particles is not a spectrum. The location of the particles is in orbitals, and that is a common word that you've heard very often. This is one of those problems where a student may trick themselves into choosing something that doesn't make sense, which is why I highly recommend, as I said, choosing an answer before you commit to hearing how I do it. Okay? And I do know that according to my analytics, there is a good chunk of you that actually do pause the problem and listen to how I do it, um, before you even make a choice. You do make a choice before you hear me give you the answer and how I go about it. Let's go on to numero tres, number three. Which change occurs when an electron returns from a higher energy state to a lower energy state? An ionic compound is formed and energy is emitted, or an ionic compound is formed and energy is absorbed, or a specific amount of energy is absorbed, or a specific amount of energy is emitted. Now, this problem, this is an what I call a 2 by 2 problem. Why do I call it a 2 by 2 problem? Because now you don't have to draw this box that I'm about to draw here, but if you draw a box here, okay, nice, okay, and now again, you don't have to draw this box, and I actually recommend that you don't draw the box. But if you notice, this is asking you 2 separate questions: ionic compound, or not a compound. And then the second one, energy is emitted. Yes, the second one says a specific amount, and the first one just says energy emitted, and the last one is energy is absorbed. And so if you notice, the one that says that an ionic compound and energy is emitted is problem one, and an ionic compound is formed and energy is absorbed is choice two rather. Then not a compound but a specific amount of energy is absorbed is three down here, and not a compound but a specific amount of energy is emitted is number four. Now, why do I call this a 2 by 2 problem? Because this question is not asking you to choose really one choice. It's actually asking you to choose 2 separate things. 1 and 2, ionic compound. Choice 3 and 4, not ionic compound. Then choice 1 and 4, and energy is emitted, and choice 2 and 3, energy is absorbed. So if you can answer any part of this question, you've increased your chances of getting the question right by 50%. So for example, if you know whether it's an ionic compound is formed or not, 50% chance of getting it right. And if you know whether energy is emitted or not, 50% chance of getting it right. And if you can answer both of those questions, you have a 100% chance of getting it right. So in this case, I note that an electron returns from a higher energy state to a lower energy state, which means that the electron is not being released by the atom or molecule. So, which means which means that we don't have a new compound being formed. So this is not the answer. Okay? So any of them with an ionic compound cannot be the answer. And now we have a 50-50 chance of getting it right. Now the second part of it is whether energy was released or emitted. If the electron went from a higher energy state to a lower energy state, remember, energy has to be conserved. The law of conservation of energy says that energy has to be conserved. So if the electron went from a higher energy state, more energy, to a lower energy state, less energy, the energy had to go somewhere. It gets released out into the environment. Literally, a photon gets released, so an energy is emitted. Energy is emitted. Energy is emitted. Cross out, energy is absorbed. And for the previous one, we checked off a specific amount of energy. And now the only one that has 2 check boxes is choice 4. So we crossed out 2 and 3 just now, and the only one that has 2 check boxes, or equivalently no X's, is choice 4. So we've gotten that one right, and we are 82 questions away from getting a perfect grade on this test. I do see the subscribe button here. If you feel that so far I've provided a few minutes of a phenomenal GOAT video, then I want you to hit the subscribe button just to show your appreciation. I do mention that one of the reasons why I do this, I do tutor JuanTutors.com. I do tutor, and if you do need a tutor for math or physics or even chemistry, or English. I don't tutor the English or the history, but I do have tutors who tutor for me in those subjects. But if you do need a tutor, JuanTutors.com. But that said, 844 subscribers. One of the reasons I do this, and yesterday I had 830 something. I've always wanted to have a portion of my content, my business, be available to everybody. I knew that as my personal prices increased, that I would start pricing people out, and that's just the unfortunate thing. The way I grew up, I never had a tutor because I couldn't afford them. So I always wanted to give something out for free, and this is the part of the business that I do for free. And the way that I get paid for it is by getting subscribers. And 123,000 views so far. All of those 123,000 views had ads on them, or a lot of them had ads on them, and not a single penny went to me, because that's the way that the system works. But if I get to the point where I get the 1,000 subscribers, then at least the revenue goes to me, and I get paid for something that I provide you for free. So that said, numero cuatro, number 4, which phrase describes the different isotopes of an element? Same number of electrons and different number of protons, same number of protons and different number of electrons, or same number of protons and a different number of neutrons, or same number of neutrons and a different number of protons. So again, this is different isotopes of an element, okay? So I do hope that at this point you do know what an isotope is. An isotope of an element literally has to be the same element, right? And if you remember what an isotope is, so it has to be the same element, right? Which means that it has to have the same number of protons. Which means that any answer here that doesn't have the same number of protons has to be incorrect. Different number of protons, incorrect. Same number of protons, different number of, okay, same number of protons or same number of neutrons and different number of protons, okay? Which means choice 4 is incorrect. Before we analyze choice 2 and choice 3, I want to talk about what I call a passing problem. Passing problem. PP. And now a passing problem, by the way, actually has the same exact definition for all of the regions. For all of the regions, and for different reasons, they have the same definition. If we look at, and I was doing some research to add to the diagram, but if we look at the scoring, allow me just a brief time to look at the scoring here. Here's what a perfect grade is: 100%. 100%, of course, is 85 out of 85 questions that you get correct. All right, but then what is a passing grade? A passing grade is a 65. Okay, which requires you to get a 51 out of 85. Now, granted that is more than half of the 85, but it's not 3/4, and definitely not less than half of the 85. And so why do I call this a passing problem? Well, because you'd need approximately half of the points to pass this test. Yes, again, 51 is not exactly half, it's a little more than half, but it is a chemistry class and it is a little bit more difficult. So yes, it's a little, technically a little bit more than half. But then if you actually start to take into account for all the extra points that you can get through other test taking strategies, I do like defining this as a passing problem for half. Now, okay, so what does it mean? Imagine if you turn every multiple choice question into a question that you have, instead of a 1 in 4 chance of getting it right, you have a 1 in 2 chance of getting it right. Well, in that case, you are basically heading right towards a passing grade. That's why I call a 50-50 chance of getting a problem right a passing problem. So every Regents, for different reasons, still a 50-50 chance of getting it right is a passing problem, because for every Regents, it's leading you towards a passing grade. Okay, so now that we've eliminated for correct reasons choice 1 and choice 4, now we could actually analyze choice 2 and choice 3 for being correct or incorrect. Now again, let's go back up. We said different isotopes of the same element. Different isotopes of the same element. It literally has to be the same elements. You know, it has to have the same number of protons. So that has same number of protons, same number of protons. Now the second one says different number of neutrons or different number of electrons. I'm sorry. So choice 2, different number of electrons. Choice 3, different number of neutrons. Well, if it has a different number of electrons, that makes it an ion versus an element. Okay? Whereas choice 3, the same number of protons and a different number of neutrons, still makes it an element. And in fact, remember, the nucleons, the particles in the nucleus, are the particles that define whether two atoms are isotopes of each other. And so this one is the one that's correct. Choice 2 is not even it doesn't even make elements. It's ion versus elements. Whereas choice 3 does confirm that these two atoms are the same element, just with a different atomic mass. Okay. Número 5, number 5. Which statement describes a chemical property of sodium? And I added this picture here to display what happens if you take sodium metal, clean sodium metal, which tarnishes very fast. So you have to make sure it's clean sodium metal, and throw it in water. If you notice, there's a fireball with sparks going all over the place. Literally, this sodium was dropped into the bath of water. So gravity is acting on it. And so this fireball was created in milliseconds, perhaps even microseconds. The amount of time it takes for the sodium, which is dropped from a higher height, to fall that distance. I mean, very fast reaction. Now, which statement describes a chemical property of sodium? One, it is silver in color, or it has a density of 0.97 grams per centimeter cubed at room temperature, or it has atoms with an atomic radius of 160 parts per million, or it is highly reactive with water. Kind of, this picture kind of gives you a hint, but if you, of course, are taking the Regents, you don't have this picture. I want to just make sure that you know that this picture is accurate. This is the nature of sodium when reacted with water. So I think you probably know the answer already. But what's wrong with some of these answers? It says a chemical property. So all the words in the problem are important. Do understand that there's many problems that do this. They tell you true things about the object in question, but some qualifier in the problem makes the answer be one specific thing. If they said a physical property of sodium, it is silver in color when you clean it, and don't let it react with the oxygen in the air. So this is true, but it's not physical, not chemical. So we cross that out. It has a density of 0.97 grams per centimeter cubed at room temperature. It's also physical. It's also true, but it's also physical, not chemical. Okay. Now this one, so now we have a 50-50 chance of getting it right. So if we're looking at this one, at atoms with an atomic radius of 160 picometers, or it's highly reactive in water. Now, if you are the kind of student like me, you might be debating the answer to this question at this point, because number 3 might feel like it's chemical, number 4 might feel like it's chemical, and you might debate it at this point. But so maybe what I might do is I might put an X here. I'm doing this because I want to teach you some notation that I use. I crossed out number 2 at the number, because I know for a fact that number 1 and number 2 are incorrect. When I'm doing the problem, I put an X next to the answer if I think it's incorrect, but I don't know. Again, number 1 and number 2 are 100% not chemical properties, so they're 100% incorrect. Whereas choice 3, I might be saying fake student me. When I say fake student me, I'm simulating myself as a student, right? So I'm pretending that I'm a student. Fake student me says, oh, atoms with an atomic radius of 160 picometers, that sounds like a chemical property, but maybe not. But highly reactive with water, I know that this is true. Which one is the chemical one? So I put a checkbox next to the answer because I think 4 is correct, and I put an X next to 3 because I think it's incorrect. Now for test taking strategy, I really should actually at this point start to debate it here. and really only move on if I really can't come up with a final answer. So, what's wrong with choice three? Choice three, atomic radius of 160 picometers, is actually, again, a physical property, not a chemical property. And I mean, like a sphere has a radius, right? That's not a chemical property. You've never seen a sphere in geometry react with water. That's a geometric property. So which makes it physical and not chemical. So the fact is it is choice four, and it is highly highly reactive with water, as you can tell from this picture. In fact, when you see sodium, it's almost always in a bath of oil, and the reason for that is that the oil doesn't let the oxygen in from the air, and in fact the oil tends to oxidize when it actually comes a little bit when it comes in contact with oxygen. So even the tiny amount of oxygen that might diffuse into oil oxidizes the oil. So number six, oxygen can exist as diatomic oxygen gas, O2 gas, or ozone, O3 gas. These two forms of oxygen have the same molecular structure and the same properties, or different molecular structures and different properties, or the same molecular structure and different properties, or different molecular structures and the same properties. Okay, so this one highly suggests, this is one of those 2x2 problems that I highly suggest choosing one before you hear me give an answer. And by the way, I'm not doing this video live. So the number of subscribers, I always like having this here. The number of subscribers can technically go down. And it does go down because people do subscribe and unsubscribe, subscribe and unsubscribe. And usually I get like 10 subscribers and one unsubscribe, 10 subscribers, one unsubscribe, but if you want to, so if you do add yourself to the subscriber list, you will not appear today because I recorded this in the past and then uploaded it. But in the future video, this does update automatically and instantly. So if I get let's say 7:04 p.m. a new subscriber, it does change to 8:45. All right. That said, highly recommend. This is one great one to train you into choosing a specific choice because it is also a 2x2. So the question is, does it have the same molecular structure or different molecular structure, or and also do they have the same properties or different properties? Now, O2 and O3. Here's the thing: if I were a student, I would try to think critically about whether I could eliminate separately, since each of the 2x2s, as opposed to eliminating any of the four choices. So I'm thinking either analyze the situation about the structure or analyze the situation about the properties. And immediately when I'm saying that to myself, I realize I can definitely analyze the structure. O2 looks like this. O bounded with an O. Okay? O3, now O3 does exist, but as you know, it's not exactly a very stable molecule. Because it's got an oxygen bound to another oxygen, but then somehow bound to another oxygen. And it'd be a fair question to ask, how is this possible? Well, again, it's a very unstable molecule, and that's one of the reasons why, for example, the hole in the ozone is such an important thing to protect, because it's extremely easy to break down literally all of the ozone that's in the ozone hole, just trivial with a few chemicals. And in fact, one of the reasons why the ozone hole got as big as it is that the chlorofluorocarbons that you've heard of, or definitely your teacher has heard of in the past, that went up into the ozone layer and started breaking down the ozone. The reason it's so dangerous is that it's not that it's just simply reacting to the O3 and just binding to it. It's catalyzing the reaction that turns O3 back into O2 and monatomic oxygen. It's catalyzing that reaction. So literally the chlorofluorocarbon reacts with the O3, takes one of the oxygens, tosses it out, and then releases the O2 and goes to destroy another O3. So a very small amount of chlorofluorocarbons can destroy the entirety of the ozone layer. So that said, the reason I analyze this as a structure is that if you see the structure here, they definitely have different molecular structures. So I put a checkbox here and I put a checkbox here. I cross out the same molecular structure and I cross out the same molecular structure. I've confirmed that choice 1 and choice 3 are incorrect. So if you're borrowing my notation, I put the X's on the 1 and on the 3 because 100% I'm looking at two different structures. They're not the same. So I know choice 1 and choice 3 are 100% incorrect. Now, the second question is, do they have different properties or the same properties? Well, I know that if the ozone disappears, if the hole in the ozone disappears, we are in trouble because we're going to get hit by a lot of UV rays, despite the fact that we're surrounded by 21% oxygen-based air. The ozone layer has a very small amount of ozone, but it does a tremendous amount. You eliminate that ozone, a tremendous amount of oxygen that we're surrounded by won't do anything with the UV rays. So they definitely have different properties, not the same properties. Also, you can actually, if you ever smell like an electrical smell, like you like have a, if you ever smelled like a frayed wire smell, that frayed wire smell, believe it or not, is not the metal. It's actually the ozone in the air. So ozone also has a special smell to it that is uh, a nice warning sign that you might have a situation that you might want to call an electrician for extremely quickly. Or if you live in an apartment, your superintendent. And it's also a dangerous molecule. It's not. It's a very highly reactive molecule. You could actually sanitize pools with an extremely small amount of ozone. Okay, which the only answer that has two checkboxes is choice 2, and choice 4 has an X. So choice 2 is the answer. And on that note, we go to numero 7, number 7. Which formula contains a polyatomic ion? At this point, I do need to go to the reference table, and I realize I did not download the reference table. Let's go for the reference table as soon as we can. Okay. Let's go for the reference table. Okay. And we go to page 2. Polyatomic ions. So this is something you want to get used to in this test. You want to grow accustomed to using the reference table as much as possible. Like if you, I and I guess I'll also say this at this point about battling with your teacher. You could battle with your teacher all you want. You could actually dislike your teacher all you want. I mean, I love learning. I don't love all my teachers, and I'll freely admit that. And I know that there's some students who don't like me, and I think that's okay. Believe it or not. But do understand that whether you like your teachers or not, they do, generally speaking, have your best interests at heart. So one of the things that I notice is that sometimes, like the teacher will battle with a student. And like the student will want to use the reference table when the teacher says no, and then the moment the teacher says use your reference table, the kid is like, nah. Let your teacher win that one. When the teacher says use the reference table, you have to. In fact, I don't know how you would do this problem if you didn't use your reference table. Really. So polyatomic ion, let's actually know what this is. So an ion is a atom or compound. I'm realizing I don't know a complex. How about a complex? A compound. I'm going to say compound. So I'm realizing that I don't know what words to use, but I'll tell you why here. An atom, quotation marks, or compound, quotation marks, which has one or more extra or missing electrons. Okay? Why did I put atoms or compounds in quotation marks? Because I realized not every polyatomic ion could exist as a compound. Some of them actually can, but not all of them can. Like they're not balanced that way. They if you literally like deionize them, took away the extra electrons that they have, so many of them would just break up. Or if you gave them the electrons that they're missing, some of them would just break up. Like they just that's the way it is. So I realized, so why am I putting atom in quotation marks? An atom with an extra or missing electron is not called an atom at that point, it's called an ion. So atom is not even the right word to use it. But this is polyatomic ion. So polyatomic ion then has more than one atom. Has more than one atom in it. So then we have to literally compare the polyatomic ions here um, to the list on that we have here, KCN. So the choices are KCN or K2S or AlBr3 or Al2O3. Okay, so if you look for the ions, let's see. So we have formula and name. We have Cn, and I'm looking slowly. I'm looking for, now K is a metal, so Cn would be the ion, and I'm looking at Cn minus, and this is potassium cyanide. Which is a salt, and it's a very dangerous salt. Whereas K2S, K2S, well, K is wouldn't be polyatomic, and S would not be polyatomic. So this can't be it to begin with. So if I'm eliminating answers, that one has to go away. So now I went from a 1 in 4 chance of getting it right to a 1 in 3 chance of getting it right. Now, fake student me might be debating which one of these answers might be it between KCN versus ALBR3 or AL2O3. But I noticed that AL2 is not in this list, and O3, 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 we looked, not on this list. So this one is not on the list. And so we look, AL is not polyatomic, so we look for BR3, BR3, BR3. So this is literally a reference table reading problem. Neither choice 3 nor choice 4 appear in the table, but CN minus does. So the only answer that's valid on this list, and even able to be valid, is choice 1. Okay? So, numero ocho, number 8. What information about C4H10 can be determined from its structural formula, but not determined from its molecular formula? The physical state, the molar mass, the ratio of different atoms, or the arrangement of the atoms. Again, which information about C4H10 can, I'm going to underline the word can right here, can be determined from its structural formula, but not determined from its molecular formula. Definitely the answer physical state can't be it, because so it's either physical state, molar mass ratio of different atoms, or arrangement of the atoms. Physical state, and again, I recommend pausing before I give the answer. I'm going to stop saying that, but I do recommend pausing, choosing an answer before you hear me give it. I want to talk about the process of elimination. That'll help you. So this kind of situation, I can eliminate physical state immediately, because you can't determine the physical state of C4H10 from the uh, from uh, from its structural formula, because cool it down, warm it up, heat it up, its physical state changes. So the structural formula can't tell you the physical state to begin with. The molar mass does make sense for the structural for the structural formula. It can be determined from the structural formula. The ratio of different atoms can be determined from the structural formula, and then the arrangement of atoms can be determined from the structural formula. So now we have 3 choices that might be the answer. Now, notice here, I put checkboxes next to all 3. Why did I put checkboxes next to all 3? Because as of now, I've gone through, used half the information from the problem, and so far they're all reasonable. choice 1, though, is not correct. Can't be. But now, with the second part, not determined from its molecular formula, how about the molar mass? Not determined, so I can't determine it from the molecular formula. Actually, the molar mass can be determined, which makes it incorrect. So actually, I should put a checkbox. Well, see, this is where I should use the word can, which is what we don't want. You know what? I'm going to change my notation a little bit because the question, this is because I realized that if a student is working on this problem, a checkbox might be a confusing notation if they're looking for something that can't happen. So I'm going to use the word can, and then the plus is going to be determining the second part. Can, and the symbol and instead of a plus because it looks like a T. Can and so can and now the second one, the molar mass can be determined from the molecular formula because you know how many atoms of each type are there. Now, suppose I'm a student, ratio of different atoms, or arrangement of the atoms. I might be debating these, so maybe I'm at 50-50. But in fact, if you have the molecular formula, you do know the ratio of different atoms. So that one is really not debatable. You have C4H10. There's the molecular formula C4H10. I know that there's 4 carbons and 10 hydrogens. The ratio is 4-10 or 2-5. So it has to be the arrangement of atoms. How could it be the arrangement of atoms, though? You might be saying, I know what C4H10 is, and it's on the reference table. C4H10, I go to, do I have it? Let's see. I know it's on the reference table. I didn't write down the number, the page number. Sorry if scrolling makes you dizzy. Please look away if scrolling does make you dizzy. Before I go here, do they have the prefixes here? No, okay, so they do not have the prefixes here. So this is butane. Right? The butane, C4H10, except it doesn't have to be butane. Butane can be written as a zigzag, is one of the ways to write butane. Or you could write butane as C, 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 and then H, 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 H. So this is butane. Okay. So you might say, well, it's butane. I know the arrangement of the atoms, but except that you could literally also just make this chemical. That instead of looking like that zigzag up there, it looks like this. Okay. And that's literally the diagram for it. That's the diagram for it if you've ever seen these kinds of diagrams. Or it could be this way. Oops. It could be this way. And literally those diagrams are valid. But what about, what is this? This is literally a carbon, a carbon, a carbon, and a carbon. And if you notice, that's 4 carbons, 3 hydrogens, another hydrogen, that's 4, 5, 6, 7 hydrogens, and then 8, 9, 10 hydrogens. That's C4H10. So this one is a perfectly valid molecule. And this is often called, I know it goes by another name, and I'm trying to remember the other name, but this is, it's got a propane base with a methyl group in the second one. So this is 2 methyl propane. And now it's bothering me too because I don't remember the other chemical name for 2 methyl propane. So if you decide to Google it, type it into the chat and let me know which one it is. But either way, 2 methyl propane and butane have the same molecular formula. Therefore, the arrangement of atom, but different arrangement of atoms. So therefore, the C4H10 cannot tell you the structural formula. So can't. Sorry, got the word can't. There we go. Um, worried for a second. Numero nueve, number 9. Which quantity is conserved in all chemicals reactions? Charge density, moles, or volume? Okay, charge density, moles, or volume. So there's a nice test taking strategy that it doesn't happen in many problems, but it is a worthwhile one to remember, because every once in a while you might be debating two answers and then realize that they actually imply each other. Therefore, they actually both have to be wrong. So, charge density, moles, or volume. Which quantity is conserved in all chemical reactions? Okay, conserved in all chemical reactions. So we're looking for conserved in all chemical reactions, charge density, moles, or volume. So if density is conserved, suppose that density is conserved. Well, by the law of conservation of mass, the mass is also conserved, right? Um, well, so if density and mass are conserved, then volume is also conserved, which means that literally, if density is conserved and then volume is also conserved, that means that they would literally be both true at the same time. In multiple choice questions, they can't be two true answers at the same time. There can't, so they imply each other. And there can't be two true choices, assuming that they wrote the problem correctly, which that is an assumption you should make, because these tests, despite the fact that there's an occasional error, these tests are vetted tremendously. So density and volume, since they imply each other, that would imply that they are conserved for all, which means that they're both conserved for all chemical reactions, which can't be true, because that would mean choice 2 and choice 4 would be the answer, which means that they're both wrong. And now we could actually use, if not only that, we could actually use the fact that volume and density are not conserved for all chemical reactions sometimes. But in this case, I don't know how that helps you with charge or density. But point is, we now have a passing problem. We have a passing problem because we've eliminated 2 out of 4 choices. So now, is the answer charge, or is the answer the number of moles? You might say, well, of course the number of moles is conserved because the number of atoms is conserved. So, but that is what's conserved. The number of moles of each individual atom is conserved, but the number of moles of compounds is not. So, for example, if you react 2 moles of hydrogen with 1 mole of oxygen, that's 3 moles of molecules. Combine them together, you make 2 molecules of H2O, 2 moles of H2O. So you started off 3 moles of molecules and ended up with 2 moles of molecules. So the number of moles is not conserved. Again, this example, 2 H2 plus 1 O2 react to form 2 H2O. And of course, 2 plus 1 does not equal 2. 3 does not equal 2. So number of moles is not conserved. But if you notice, in all chemical reactions, the number of protons doesn't change. The number of neutrons definitely doesn't change. The number of nucleons doesn't change, but also the number of electrons doesn't change, because there's also a law of conservation of charge. In a closed system, the charge can't just disappear. So charge does have to be conserved. The law of conservation of charge says that charge has to be conserved. Okay. Número 10, number 10. What do the coefficients in a balanced chemical equation indicate about the substances in the equation? So interesting, I have a balanced equation right here. So does it say, does it mean the mass ratios or the mole ratios or the empirical formulas or the molecular formulas? So what do the coefficients in a balanced equation mean? So at this point, then we have to define what the coefficients are. So the coefficients are the numbers in front. Okay, so that's a coefficient, that's a coefficient, and this is a coefficient. Okay, so what do those coefficients imply? indicate about the substances? Does it imply the mass ratios or the mole ratios or the empirical formulas or the molecular formulas? Well, here's the thing. If it was the mass ratios, that would imply that I have 2 times more hydrogen in mass than I have oxygen. But hydrogen is a very light element, approximate atomic mass 1, whereas oxygen, and so hydrogen H2 has an atomic mass of 2, whereas oxygen has an atomic mass of 16, so O2 has an atomic mass of 32. So these do not match the 32 and 2 or 32 and 4, or don't match each other. No. So the mass ratios is definitely not the answer. The mole ratios is starting to feel really good here, though. Now the empirical formulas um, is refer, and I'm going to be talking about this later on. So, but an empirical formula is a formula. It's a chemical formula with the indices, with the subscripts, the indices, the two reduced to by the greatest common divisor. The empirical formula of H2 is just H. The empirical formula of O2 is O. The empirical formula of H2O is H2O. But the molecular formulas, is determined by the subscripts. So that's not it. So why not the empirical formulas? Again, because the empirical formulas are involve the subscripts. So the mole ratios is definitely the right answer. 2 moles of H2 plus 1 mole of O2 make 2 moles of H2O. Okay, so numero 11, number 11. At STP, which substance has a metallic bonding? Argon, barium chloride, sulfur dioxide, or titanium? Metallic bonding. Okay, so you have to think about what a metallic bond is. And what kind of molecules have metallic bonds? Metals. So we have ionic bonds, we have covalent bonds. For water, we have hydrogen bonds. And then we have metallic bonds with metals. Those are the 3 ionic covalent, 4 types of bonds that we have. Metallic bonds only occur in metals. So what is a metallic bond? Literally, metals come together, and instead of, let's say, for example, sharing electrons, or instead of, which would be a covalent bond, or instead of one atom literally stealing an electron from another atom, which would be an ionic bond, or the extreme attraction of a hydrogen bond for H2O, the hydrogen on one molecule to the water on another. This is a metallic bond where the electrons in metals, instead of being bound to any one atom, the electrons form a sea of electrons in one collective uh, um, energy level. So the electrons can literally hop anywhere within the metal, and they can flow. That's actually, in fact, what makes a metal a good conductor at room temperature. So which ones have metallic bonds? Well, argon has no bonds. Argon is a noble gas, which means it's basically no bonds. Barium chloride. Let me see if I wrote what kind of bond this is. Barium chloride. I didn't write what kind of bond it is, but it's not a metallic bond because it's not a metal. Sulfur dioxide is a covalent bond. Oh, so this is I did write it down. This is a salt, which means it's an ionic bond. And sulfur dioxide is a covalent bond. And titanium is a metal, which means it has a metallic bond. Okay, and now you know that metals have metallic bonds, and only metals have metallic bonds. That's an important thing to know, and we have a definition that gets us the answer right away. So numero 12, number 12, how many pairs of electrons are shared between the nitrogen atoms in a molecule of N2? 1, 2, 3, or 4? It does help to know the answer to this question. There is a rule when you look at the reference table. If you look at the periodic table, all of the elements in group 17 have 7 electrons in their outer shell. So they, well, except for an unknown number 17, 117, which the this test does give us the name of element 117 later on, so we'll talk about that then. So that's the only one that's not known. In fact, I think um, for some reason this one is not included. Maybe the half-life of this one is too short. I don't know. But all of these have 7 electrons in their outer shell. So when they bond to each other, generally speaking, they bond sharing 1 electron each. The ones in group 16, like O2, they share 2 electrons each. S2, 2 electrons each. Se, 2 electrons each. Te2, 2 electrons each. And the ones in group 3 share 3 electrons each. N2 has 3 electrons. So the N2, if you draw it out, you could draw it out this way. Okay. And so these share 3 electrons each. So that's the one that makes sense, being in group 15. So 3 electrons shared in a diatomic molecule. Okay. So it's not 1 or 2, or definitely not 4. Okay. So which formula represents a molecule with an asymmetrical distribution of charge? An asymmetrical distribution of charge. Cl2, CO2, CH4, or H2O. There's one answer that I know. I know this one because it's an important one to actually know how the charge is actually asymmetrical. But if I didn't know how to do this problem, I would eliminate this one immediately because Cl2 is literally a diatomic uh, molecule. Like it's literally chlorine bonded to itself. Uh, so it shares it. There's no way that one of the chlorines uh, takes the electron more strongly than the other chlorine. Uh, that's not mathematically feasible. Okay, so this structure is very symmetric. Okay, CO2, H2O, and CH4. Now, I see why there might be a lot of debate on which one of these it is, but there's two that that come up a lot that are important to know their structures. Why, for example, given we know that CO2 is the chemical that we breathe out after we've breathed in some nice oxygen. The air that we breathe in is 21% oxygen, and it's about 69% nitrogen. Notice that already adds up to 100. The other elements in the air are trace amounts, including carbon dioxide. Yes, carbon dioxide, despite being a greenhouse gas and a very potent greenhouse gas and affecting global warming, is actually in the air in very trace amounts, which is one of the reasons why we actually have to be very careful, because the carrying capacity of the atmosphere to carry carbon dioxide is extremely large. So we do have to be careful not to release too much of it into the atmosphere. That said, why is carbon dioxide a gas while water, H2O, is a liquid at room temperature? And in fact, not just at room temperature, but at quite high temperatures to 100 degrees Celsius. Um, well, because of hydrogen bonding. And so I'm actually adding extra information here about water. So water has an oxygen bonded to 2 hydrogens. And then the oxygen has then 4 electrons that kind of sit on the opposite side of the hydrogens. So as a result, the side of the oxygen that has the electrons has a slight negative charge, and the side that has the hydrogens, remember hydrogens only have 1 electron. So if that electron is strictly caught between the hydrogen and the oxygen, then the electron is not to the left where the hydrogen is, which means that there's no negative charge on this side, which means that this is mostly a positive charge, and this is mostly a positive charge. This is a highly asymmetric arrangement of charge. And in fact, this is the cause of hydrogen bonding. Why, for example, you might have another OH close to this, and then there's minus, minus, minus. There's an attraction here. There's an attraction there, which is a hydrogen bond. And it's due to the asymmetric charge. So why is the answer C, not CO2? Well, if you look at O and H and H, H2O, water, is a bent molecule. But carbon has 4 valence electrons, and oxygen. Carbon can react those 4 valence electrons, whereas oxygen can actually attract 2 electrons each. So as a result, you get carbon attracting those 2. Letting those 2 electrons get attracted to the oxygen, and then on this side, another oxygen attracts the other 2 electrons, and you get this nice symmetric molecule. And there are no more extra valence electrons for the carbon to have on top or on bottom. So this atom is highly symmetric. So it's not this one, it is this one. And but what about CH4? CH4, again, carbon has 4 valence electrons, so an hydrogen would love to give away its valence electron, and it does so to the carbon, which makes a nice symmetric methane. Now this is a 2-dimensional version, but the 2-dimensional version has symmetry, and so you could see that the charge is distributed symmetrically. And in fact, the 4-dimensional version is it's even more symmetric. It's got tetrahedral symmetry. If you look at a tetrahedron, the 4 corners of the tetrahedron have a hydrogen atom, and then the interior of that tetrahedron has a single carbon. So that's why CH4 does not have an asymmetrical charge distribution. Okay, on that note, we go to numero 14, number 14. Given the equation representing the reaction I2 arrow reacting to form I plus I, what occurs during this reaction? Is energy released and a bond is formed, or energy released and a bond is broken, or energy is absorbed and a bond is broken, or energy is absorbed and a bond is formed? Okay, so this is a 2x2 problem. Is the question, is energy released or absorbed? Separately, is a bond formed or broken? 2x2. So if I could answer each one of these questions. So what happens to a lot of students today when they get to this question is they try to answer which one of these 4 choices makes the most sense, when in fact what a student should do is say which pairs of which separate sets of answers is true. Is the energy released or is the energy absorbed? And then separately, is a bond formed or is a bond broken? Now, I2 forms I plus I2, there's a bond here. And here, there's no bond. So clearly, a bond is broken. And one of the reasons why I recommend that you choose an answer on your own is that you can easily trick yourself into believing something that doesn't necessarily make sense. But you know at this point what a bond is. I and I don't have any bonds between them, so a bond is definitely broken. So what does occur? It's not true that a bond is formed. It's not true that a bond is formed. It is true that a bond is broken. So we have choice 1 and choice 4 are 100% incorrect, and we have a passing problem, which is great. So now the second question is energy released or is energy absorbed? And this is an important one to know. All of these elements in group 15, 16, and 17 often appear in nature in diatomic forms. In fact, basically always appear in diatomic form. You I mean, I don't quote me on this. I don't actually know if oxygen in monatomic form is even stable at room temperature. I don't know that. I do know that you give it a little spark and that oxygen will react. In the atomic oxygen will react to form diatomic oxygen. It's in fact the reaction between oxygen is so strong that out in the universe you usually don't see, except for like inside of stars, you usually don't see oxygen by itself. Just being near oxygen is enough to make them react in nature. So well, why am I saying that? Well, although it is true that generally speaking, energy is released when a more stable molecule is formed. It's actually what is true is that entropy is created when a more stable molecule is formed. Um, However, it also is true that it's almost always the case that when a more stable molecule is formed, energy is released. So, in the other direction, when you take a chemical and in its less energetic form and break it up, so if you react them, it releases energy. That means when you break them up, it has to absorb energy. So energy definitely has to be absorbed, not released. The only one that has two check boxes is choice 3. And notice I did that by doing a 2 by 2 problem. I asked separately, before we do numero 15 number 15, I asked separately, is a bond formed or broken? That gave me a 50-50 chance of getting it right, created a passing problem. And then I asked separately, is energy released or absorbed? And then that gave me the final answer. Numero 15 number 15, the electronegativity difference between the atoms in a molecule of HF can be used to determine the energy of the molecule or the functional group of the molecule, or the polarity of the bond in the molecule, or the volume of the atoms in the molecules. So definitely pause this question. I'm gonna recommend for this one, if you need to do something with it, yes, again, you should choose an answer before you hear me do it. But I'm gonna recommend to you to see if there's any answers that you could eliminate, choice 1, choice 2, choice 3, or choice 4. But I'm gonna continue with it because of course this video is gonna be a bit long. We're gonna gung-ho right through this video and we're gonna be champions and get a perfect grade by the time that we're done. But now what is a functional group here? Choice 2. A functional group is a part of a molecule that is related to itself and given a name. And why? Because it reacts as a single atom would react. So for example, a methyl group is like a CH3, let's see, minus, CH3 minus. So, okay, so it's not a functional group because that tells you how a certain group of elements bound together, a certain group of atoms bound together react with other molecules. So it's not that. But how about the energy of the molecule? The energy of the molecule, the electronegativity difference can inform about the amount of energy, but it doesn't determine the energy. So this one it can inform you about the energy. So fake student me might not be sure, but I might put a checkbox with a question mark. Now, fake student me, real teacher me, of course, knows that choice one can't be the answer, but maybe fake student me is debating whether that makes sense because I know chemicals with a higher electronegativity have a stronger bond. Um, but then how about the polarity of the bond in the molecule? Actually, then this though I'm liking this a lot better because I know that electronegativity actually has an effect on the direction of the bond, how much of an electron that a chemical absorbs. And then the volume of the atoms in the molecule. This does not inform about the atoms, number of atoms, or the volume of the atoms in the molecule at all. In fact, the volume of the atoms in the molecule has to be determined in different ways. So then that leaves me, fake student me, with one of two choices. And then I have to think about whether the energy of the molecule or the polarity of the bonds in the molecule makes the most sense. And then I start to think about, well, actually, you can create different chemicals with the same electronegativity, but with different energies in the molecule. And then I realize, actually, it's not just the, this is not just referring to the bond, it's actually also referring to just the energy in the molecule itself. So that the energy can be changed by just heating and cooling, but even the bond itself can have a different amount of energy based on the electronegativity. So it can't be this one. This one's looking less. Now notice I hear because fake student me is not sure. Fake student me is not sure. Real teacher me is sure, but fake student me is not sure. I put the X next to this one because I'm feeling a lot more confident about choice three, and this is the one I'm going to end up choosing. But it is choice three. The polarity of the molecule is determined by the electronegativity. Okay, and in fact, there's more that we could say. Nonpolar covalent bond. So if you look at the electronegativity uh, charts on the reference table, there is electro control F, electro. No, didn't let me search for that. Electronegativity. Why didn't it let me search for that? Lame. Okay, so let's see the electronegativity. I want to see if they give us numbers. I don't think they give us numbers. They give that table that we just saw a second ago is uh okay. So let's look at the electronegativity here. Okay, so the electronegativity is here. So the electronegativity difference tells us the polarity. And so, for example, the reason that, again, we already know that Cl2 is a symmetric molecule, Cl2, because it's literally two chlorines. But if you look at the electronegativity, the electronegativity difference is literally 3.2 minus 3.2, which is exactly zero. And that's true for every pair of identical atoms. So Cl2 is very extremely nonpolar. If the electronegativity is not, the difference is not zero, it's not that there's no polarity at all, but the polarity is minuscule. So if the non-polar covalent bond has a electronegativity um, difference between 0 and 0.4, okay? A polar covalent bond has an electronegativity difference of, let's say, 0.41 to 1.69. So that means that the electron is not being shared evenly at all. It's highly leaning towards one side versus the other. But what happens if the bond goes above 161? Then that's when you get an ionic bond. When the electronegativity difference goes above 1.69, so let's say 1.7, let's let that go to infinity. Although I mean it can't really go to infinity, but theoretically there's no limit. We just have a finite number of molecules, right? So there is a limit that exists, but theoretically there doesn't have to be one. And so an ionic bond, in an ionic bond, the electron is not just being shared, but way more unevenly. The electron is literally taken by one atom from another atom, and then you get an ionic bond. And in those cases, that's when you get salts. Okay. So now we know about the electronegativity and what makes different types of molecules. Now, the electron, number 16, número 16, which sample of matter is classified as a mixture? NaCl, solid, or CH3OH, liquid, or SO2 gas, or KNO3AQ. If you don't know what these letters mean, highly recommend the S, L, G, and AQ. I highly recommend looking these letters up. S stands for solid. L stands for liquid. G stands for gas. And AQ stands for aqueous solution. Aqueous solution means dissolved in water. Okay, so now, which sample of matter is classified as a mixture? If your temptation is to say that, well, the one that is a mixture is the one that has a lot of different types of atoms, well, you're kind of out of luck on this one, aren't you? And that's a favor to you because they're all a mixture, or they're all a combination of a lot of atoms. So this problem does do you a favor. It actually makes it an easier problem. They all have a lot of different molecules, a lot of different atoms. So the one that is a mixture has to be the one that has something that's strictly unique to it. NaCl solid is pure table salt. Okay? Pure table salt, not a mixture. CH3OH. So again, a mixture, as opposed to a compound. A mixture is a collection of atoms or molecules mixed but not chemically reacted. So in CH3OH liquid, the atoms are chemically reacted. That is CH3OH is methyl alcohol. SO2 is sodium dioxide. That is not a mixture because it's pure. But the KNO3 aqueous, why is the KNO3 aqueous a mixture? Well, this one is literally KNO3 and water aqueous, H2O, mixed. And the KNO3 and the water are not reacted. So that's the only one that is a mixture of molecules or atoms mixed but not chemically reacted. Okay? Número 17, number 17. At STP, which property of tungsten remains the same for all samples of tungsten? Density, mass, surface area, and thermal energy. So I got caught on this one. Meaning like there were two answers that felt like they made sense to me. And I know now what it is that I was missing. Clearly, I was missing something. This problem is very well formed. And in fact, I looked up, interestingly, because I want to make the GOAT of all videos, I didn't just take and accept that I didn't know the answer to this question. I went all over the place to look for an answer. And literally every video of this Regents of someone doing this Regents that I found gave an explanation for what the answer to this question was. That wasn't complete. And many of them just didn't make sense. So interestingly, I can confirm that I am not the only person that got caught on this question. In fact, every person who did this problem that I saw at least got caught on this question. So at STP, which property of tungsten remains the same for all samples of tungsten? Density, mass, surface area, thermal energy. Well, eliminate the ones that you could think don't make sense. Okay. And I actually should have known what the answer was. Remains the same, right? I should have known the answer just based on the answer choices. And so, in other words, the thing that caught me is already technically embedded in the question. But the parts that I know do not necessarily remain the same. I could take tungsten and turn it into a sheet. And tungsten, being a metal, I could turn it into a quite wide sheet. I could take a literally a gram of tungsten, and if I had and just an unreasonable amount of time and accuracy, I could paper this entire wall with tungsten, with 1 gram cube of tungsten. Of course, I don't have the patience nor the luxury. But the surface area, in other words, the point is that a cube of tungsten and a flattened out sheet of tungsten uh, do not have the same surface area. So if even fake student me is able to eliminate that quickly by just hammering it out and making it spread out. So then the thermal energy, mass, or density. So the one that I eliminated and that should have given me a hint to this answer is the mass. Okay? I eliminated this one because, of course, I could have a gram of tungsten. It says which property of tungsten remains the same for all samples. Of course, if I have one sample of tungsten on top of this timer and a subscriber and advertising my YouTube channel, JuanTutors.com, and my website, JuanTutors.com, or I could have a piece of tungsten that I make this giant Rubik's Cube out of. Those masses are not the same. That should have been a hint between density and thermal energy. The problem that I ran into was the thermal energy one. I'm like sitting there like, how could thermal energy or density be eliminated? And then I started coming up with silly reasons, like trying to justify why one of them or the other might be eliminated. What I didn't realize, though, is that if I have more tungsten at STP, so standard temperature and pressure, but standard temperature, a larger mass of tungsten has more thermal energy. So it's not thermal energy. This is the one that I should have eliminated, but I didn't. So I was debating between density and thermal energy. A 1 gram mass of tungsten, yes, its thermal energy is going to be the same, but the both a 1 gram mass and a Rubik's cube mass, not the same density. Okay, I'm sorry, a 1 gram mass and a Rubik's cube mass don't have the same thermal energy. So it is density. And so what we're saying is that I talked about hammering a sample of tungsten. You might say, well, hammering the tungsten changes its density. But what hammering the tungsten does is not that it changes its density. The atoms of the tungsten literally slide around each other, and because the bond between the metals is metallic, they're able to slide by each other. And so until you kind of make a sheet about as thin as you possibly can. At that point the density never changed. The atoms aren't like farther apart than they used to be. So it is density that doesn't change. Thermal energy, again, larger mass implies a larger thermal energy. And you can vary the mass, but you can also vary the surface area, make a sheet of tungsten. Or if you start with a sheet of tungsten, make a cube of tungsten. Okay, número 18, number 18. An element is composed of atoms that must have the same atomic mass, the same atomic number, or different number of protons, or different number of electrons. An element. An element. Composed of atoms that must have. Well, we've already talked about isotopes. like I really want you to remember isotopes. Elements elements have to have the same number of protons. Okay, same number of protons to be to be an element. Okay, the same number of protons. Every hydrogen has exactly one proton. Oxygen has 8 protons, right? No matter what. And the atomic number, that's in fact was the genius thing that allowed the discoverer of this organization of the periodic table to realize that some elements were missing because the number of protons in some atoms didn't quite match. He realized that when he organized them this way by number of protons, there were just gaps that were missing, and pretty quickly a few elements were discovered, and then some of the elements were a little bit harder to discover. And by the way, one of the reasons why some of the elements were so hard to discover is that many of them have such similar chemical properties and superficial physical properties. You know, like silverish, like metals tend to be like silverish, although or grayish. I know gold is very golden colored. Most metals tend to be kind of silverish, and they turn to tarnish the same amount. Uh, and all these properties that they have, they tend to just be extremely in common. So especially like 3 to 12, group 3 to 12. Oh my God, so many. Of course, mercury is liquid, but you mix mercury with some other metals, and it just stays. The mercury just literally absorbs it. You could take gold, throw it into mercury, and the mercury literally just dissolves the gold. And you if you didn't know any better, they would still be uh if you didn't know any better, what's going on here? If you didn't know any better, they would it would you would still have a pure sample of mercury. The only thing is that they react differently. So to discover these elements, you literally have to do a lot of interesting chemical reactions. But look at iridium and osmium, +3 +4 +3 +4. Their atomic masses only differ by 2, and if their atomic masses differ by 2 and they're light elements, great. That's a huge percent difference. But 190 versus 192, literally the same type of reactions occur in both of them, etc. You know, you get it. Um, anyway, so an element has to be composed of the same number of protons. Therefore, immediately we're gonna cross out choice 3 and different number of electrons. Well, then in an element, in an atom of an element, the number of protons and the number of electrons are equal. So immediately we're gonna cross out this. Right, and it also to be an element it has to be composed of different numbers of electrons. Literally, all of the atoms have just different numbers of electrons or different number of protons. That doesn't make sense. Okay, so the same atomic number and the same atomic mass. Again, oxygen on average has an atomic mass of 16, but that's on average because the number of protons is what tells you what the element is. The atomic mass is the or the rather the mass number is the sum of the number of protons plus the number of neutrons. So the atomic mass is equal to number of protons plus the number of neutrons. Whereas the atomic number is equal to the number of protons. And since all oxygen have 8 protons, same number of protons, it has to be this one. Okay? I know that some of you may have debated atomic mass, and as I said, I commend you for having chosen a one because that means that you took my recommendation and always chose one before you heard me give the explanation. But the atomic mass can vary because, for example, carbon 12 and carbon 14 are both have 6 protons, but carbon 12 has 6 neutrons and carbon 14 has 8 neutrons. Okay, número 19, before we talk about snacks. Compared to a 2 molar aqueous solution of potassium iodide, Ki, at 1 atm atmosphere, water at 1 atm, 1 atmosphere has lower boiling point and lower freezing point, or a lower boiling point and a higher freezing point, or a higher boiling point and a lower freezing point, or a higher boiling point and a higher freezing point. Another 2x2 problem. It's asking, does an aqueous solution of potassium iodide, water, and potassium iodide salt, or water, pure water, at 1 atmosphere, without that salt in it. Does that, which sample of water, the salty water, which I don't remember, I wouldn't recommend drinking it, but the salty water or the non-salty water, the distilled water? Which one has the, does the distilled water, the pure water, have a lower boiling point or a higher boiling point? That's question one. Question two, does the distilled water have a higher freezing point or a lower freezing point? Two separate questions. Treat it as two separate questions, and they might actually give you some intuition. This is what I know. Suppose I didn't know that what kind of salt is used to dissolve ice on the road. I know, and there are more than one salt. The one salt I use, I believe, is like calcium chloride, or it might be a mix of salts containing mostly calcium chloride. But I know that the salt has to dissolve the ice and somehow not let it freeze again. So, if that salt makes it melt and not freeze again, what if this salt does the same thing? So my prediction is that the salty water implies that it has a lower freezing point, so that the ice melts but doesn't refreeze, and the pure water has a higher freezing point. By the way, this is another one that I saw two videos. This one I didn't see multiple videos. I saw two videos on this one, and the explanation on both of those videos were just not correct. And in fact, they were nonsensical. They talked about what happens when you add salt to ice, and they implied the exact opposite of the correct answer. In fact, again, the pure water has a higher freezing point. The pure water has a higher freezing point. Okay, so higher freezing point. In fact, at 0 degrees Celsius, whereas the salty water freezes at some negative number of degrees Celsius. So higher freezing point, lower freezing point, cross that out. Lower freezing point, cross that out. Higher freezing point, put a checkbox on that. Now we're left with choice 2 and choice 4. 2x2 question, as we said, and it's a passing problem. That's the benefit of looking at it as a 2x2 question. Again, you don't have to draw the box, the 2x2 box, but you'd have to recognize it as a 2x2 question. They're asking about boiling point and separately asking about freezing point. Wow, 123,000 views. I just saw that out of my corner of my eye. Now, so the second question, lower boiling point and higher freezing point. This is one that I happen to know. If you add salt to water, if you add salt to water, so and this is important. This is important to know. If you have boiling water and you add salt to water, you might see it like vigorously boil, and you might fool yourself, unfortunately, into thinking that that implies that the boiling point was like maybe lowered because it just boiled really quickly. But what's going on there is that when you add salt to water, the dissolving process is extremely violent, and the salt itself creates nucleation points in the water. And so in other words, the salt is dissolved violently. So small particles of salt are created. The tiny particles of salt give nucleation points for the water, and then the water, as a result, boils instead of just boiling at the bottom like boiling water does. It boils everywhere in the pot, and so you get just this enormous burst of boiling before the boiling goes back to a normal amount. So that's the reason why salt water. Well, why when you add salt to water, it just suddenly boils really fast. It's not because the boiling point went down. In fact, if you take a thermometer and very carefully measure the boiling point of salted water, the boiling point goes up an extremely small amount. Higher boiling point, not lower. Okay? Not lower. It is a higher boiling point. And so it's so funny. Before we talk about numero 20, number 20, if you don't want to hear about snacks, you know what? Go ahead and skip to number 20, numero 20. But I do want to talk about snacks. But the funny thing is, I was watching a cooking video out of all things, but it's like science and cooking. It's also so it's like the science of cooking video, and the guy was talking about how he just he polled people what happens when you add salt to water, and almost every chef believed the opposite of this answer. But unfortunately, it's not the chefs that are right, it's the chemists. The chefs observe an extreme amount of boiling and then assumed that the boiling point must have gone down. And that's why the insane boiling happened. After all, there are situations in which that insane boiling happens because the boiling point went down. Not this one, though. Again, this one happens, the insane boiling happens when you add salt to water because the salt dissolves extremely vigorously. You get like a violent amount of dissolving. The tiny particles of salt become nucleation points for the water and for the water to boil off of. And so the water boils everywhere in the pot instead of just at the bottom of the pot. That's what happens. And that's why the violent boiling happens. But the boiling point when you add salt to water does go up. So it is choice 4. Let's talk about snacks. Not a snack, the snacks you could bring to a test. Um, I'm talking about this because sometimes you bring a snack and it just doesn't work for you. It makes your stomach feel icky, or something like that. You don't want to bring anything that makes your stomach rumble too extremely. You might say you want to bring something with a lot of sugar in it, but the problem with having a lot of sugar, it often has a lot of fibers that can make you need to go to the bathroom. Um, I recommend this bar. This is and Pure Protein does not sponsor me. And I always say it in this video, if they want to call me to sponsor, I would love it. Um, and then I would recommend it thoroughly. But this bar has it's uh, 50 grams, and of the 50 grams, it has 18 grams of carbs. And you might say that's a lot of carbs, and it's actually one, it's not because of the protein content. It's 20 grams of protein. But two, you for a test, you actually do want a little bit of carbs. It gives you energy, so you do want some carbs in there. And the protein, though, the fact that it has protein in it lets you digest it slowly, so it doesn't make you like have to run to the bathroom usually. And also, the dietary fiber is only 2. If I were doing this just as a health snack, I would say that the dietary fiber could be higher, only because the dietary fiber helps with digestion. You don't want it to help with digestion. You want to eat it and have it not help with digestion while also giving you a little bit of boost of energy and take away the hunger that can be distracting. And it has about 5 grams of fat, which is not bad at all. That's phenomenal. And actually, the fats give you a little bit of energy. So this is actually a good bar to go for when you are taking a test. The second one I recommend, if you're in New York, if you go to a Costco or a BJ's, this is a very commonly found protein shake now. This one, and they have a bigger one. Either one of them is okay, but I like these because these are Fairlife. I like these because they come in a pack of 12 or 15, depending on the day I go and depending on the store I go to. And they're like $2 each for a pack of 12. If you buy them individually, they're like $5, which is insane. But it's worth the money if you're going into a Regents. So if you're poor or rich or middle class, spending the $5 on a snack that isn't going to make you get the runs in the middle of the test is a great snack. And the good thing about this one, and this is an important thing, even if you're not lactose intolerant, you don't want to drink anything with lactose in it because it can give you gas, and it can make you have to go to the bathroom. And if you have to go to the bathroom, you may have to miss part of the test taking's time. So let's just be honest about it. So Fairlife is lactose free. It says it right on the bottle in the tiniest letters. I'm not going to show you. You're just going to have to trust me that the Fairlife is lactose free. So it's not going to do that to you. And it also, again, 30 grams of protein. This was with an extremely small amount of carbs, so it doesn't give you the kind of boost of energy that other things might give you. And fats, 2.5 grams, again, same thing. But it does give you a little bit. And the big thing that it does is it takes away the hunger and it hydrates you a little bit. Okay, so that's why I recommend this one as a snack. Now, this one, let's talk about this one here. This would be coffee, and you see me drinking it, and it's whatever o'clock at night that's going to say in a couple of minutes. There it is. But that's my recording time. So I'm recording at 8:20, and I'm only about a third away, a quarter of the way done with this test. Woo! Okay. Um, Here's the thing, though. I am a coffee drinker, practically professional at it. Um, if you are not a coffee drinker, don't like get yourself accustomed to drinking coffee so that you could bring coffee to the test. That's not going to work for you. Um, you don't want to be accustomed to coffee. In fact, that's not actually a good thing. Um, you can here and here's the thing. I drink regular coffee because it energizes me. If you are not a coffee drinker, the coffee can make you unreasonably hungry, like hungry to a level that you've never even felt in your life after not eating for 2 days. You could literally have had a good breakfast, drink coffee, and get starving. And if you talk to adults, they're like, well, coffee actually makes me full. There is some weird brain stuff that turns coffee into fullness for professional coffee drinkers. And it's one, it's real because you feel full, but two, it's fake because it is. And if you look at how adults eat on days that they drank coffee versus the way adults eat on days that they didn't drink coffee, there's the proof. On days that they didn't drink coffee, they eat healthier. On days that they did drink coffee, they run for the sugars. Literally, that's what ends up happening. So even adults who think it fills you up because they're right, because it does fill them up, they're actually only 20% right. Their feelings are only 20% right. Their actual state is 80% wrong. Um, but does it mean you shouldn't bring coffee with you? Actually, so first off, this is a sealed container. Okay, so it's safe. Press it, drink, unpress it, lock it, done. But if you actually bring decaf coffee and you're not a professional coffee drinker, decaf coffee is going to do a phenomenal job at what regular coffee does for me. Decaf coffee does have caffeine. Again, decaf coffee does have caffeine. But here's the thing, it's kind of the same thing. Even a small amount of caffeine is gonna, and I'm not recommending you take caffeine because again, it is a drug. You have to get permission. It is technically a drug. I mean, you really have to ask permission. Um, and you have to think about its effects. In fact, I would even do a dry run a couple days before, have a decaf coffee and see what happens. But the other thing is, remember what I said about the lactose. Fairlife doesn't have lactose in it. It's lactose free. If you put regular milk in your coffee, even if you're not lactose intolerant, you might regret it. Highly recommend using lactose free milk. Should you put sugar in it? Yeah, sure. Today is not the healthy day. Today is the you're taking a Regents day, right? You want to put however much sugar makes it taste good? Great. Milk, lactose free milk. Okay. Do not take regular coffee if you're not a professional coffee drinker. That's your snack advice. And the last piece of snack advice, this is not a snack. Your meds. This is my Weezer squeezer. I freely admit that I have asthma. There ain't nothing wrong with asthma. If you have any meds that you're supposed to be taking, take them with you. Make sure you have them. Your school probably allows you to carry your inhaler with you. I would imagine that they do. I carry my inhaler with me all the time. Sometimes I'm teaching, blah, 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 blah. And then I hold my breath for a few seconds. And then I use it. I've even used it in the middle of tutoring videos. I kind of feel it like in about an hour, I might be using my inhaler. Uh, that's just a thing. So any meds that you normally take, bring them with you. Any illicit non-medication drugs, I recommend avoiding those because even if they're good for people who get prescribed them, it's hard to predict the effects that they would have on you. And the last thing you want is to take something illegal and go into a test and admire the structure of the paper on which the test is printed more than the meaning of the words that are on that paper. And I've seen that happening. So on that point, we are going to go to numero 20, number 20. Which statement sorry, let me start that over. Número 20, number 20, which statement describes the particles of an ideal gas based on kinetic molecular theory? Do the particles have an attractive forces between them, or they move at random, constant, straight line motion, or particles collide increasing the total energy of the system, or the particles are separated by distances that are small compared to their size. All right, so definitely I know um, I know a little bit about ideal gases. So there are two that I crossed out pretty quickly. So fake student me says that particles have an attractive, this is ideal gas. Do particles in an ideal gas have attractive forces between them? No, they have zero forces between them in an ideal gas. Remember, ideal gas. In real gases, do the particles have attractive forces between them? Sure. Van der Waals forces. But do ideal gas particles have attractive forces between them? No, zero. And then the next one, choice 3, the particles collide, increasing the total energy of the system. So the energy is constantly increasing in the system? Till what? Till no end? Just till infinity? No. In fact, the particles don't collide at all. They're not even like billiard balls. Imagine like they're like billiard balls that just pass through each other and do not interact at all. The particles don't collide, in increasing, keeping it the same, keeping the energy of the system constant. Okay, unless you modify the system. So fake student me already eliminated choice 1 and choice 3, and now fake student me might be stuck with choice 2 versus choice 4. The particles move in random, constant, straight line motions. That one feels good. Random, constant, straight line motion feels good for fake student me. But then I read choice 4. Fake student me says the particles are separated by distances that are small compared to their size. And that one feels good to me too. What's wrong with one of these? I'm sitting there staring at it. And then a fake student me might actually gravitate towards choice 2 anyway. And that's going to be the correct answer eventually. But because I do know that in an ideal gas, the particles still move, and they do move randomly, and they do have constant motion. They do have straight line motion. They're not parabolic motion, like they would be like on the surface of the moon. But because the container is too small for there to be parabolic motion. So what about the small compared to their size? What's wrong with that? The particles are distances that are the particle. Then I read, and this is what happened to me, that when I was reading this problem, this is what happened to me. I read choice 4, and I said that the distances are small compared to their size, and I went flop to the front of my head. The distances are large compared to size. The distances are large compared to their size. One of the reasons that an ideal gas, why gases behave like ideal gases, is that their distances are extremely, extremely large compared to their size. So what happened when I read this problem is I read it as I read it to you just now, and literally the concepts just kind of switched. So what happens in that situation? How do I fix that? First off, is there a hint there that maybe I have a little bit of a reading writing issue? And I actually do, and many of you do too, undiagnosed or diagnosed. So what do I do? What do I do in this case? When I'm writing notes, I write this one: distance that are small compared to the size. I write that symbolically because symbolically I might be able to understand this better. In fact, maybe I understand it better that way because I'm a math person, but maybe I write this. Distance is less than the size. That doesn't make sense because that would mean that the atoms are really close together and they're interacting a lot. And so then that's when I realized that this answer is very wrong. In fact, all of these answers are extremely wrong except for this. So had I read this correctly the first time I did it, it would have been a gimme problem. Because none of the answers made sense at all. In fact, all the other ones had the exact opposite properties that an ideal gas has. So what's the lesson here? Before we read number 21, I just want to be clear. There is a lesson. The lesson here There's a lot of problems that do this to you in this test. They are not trying to trick you. They're asking you to compare two different things, and there's nothing wrong with that. There's just a finite number of ways that you could ask somebody to compare one thing to another. So what do we have to do when they ask us to compare things? We have to also pause and think about which thing are we analyzing. They'll say things like compared to like H2O, H3O plus, something something, or compared to H3O plus, H2O something something something. So, and they'll have multiple choices about the thing that they want you to address. You have to pause for a moment and make sure you're addressing the thing that they're asking. If two answers make sense, make sure that there's no switching of things accidentally. Make sure that you're understanding the content of the problem fully. Often another thing that you need to do is maybe you need to go back into the problem and make sure that you read from the problem number to the last character on the question so that you didn't miss any part of the question. One thing that I didn't address is that in the elementary school, we did a disservice to our students by teaching for like half the year to cross out irrelevant information. Why was that a disservice to students? Because we taught students that there's always going to be irrelevant information in problems. And here's the thing, there's almost never irrelevant information in a problem. I don't know if you noticed that there was one problem, there was one tiny piece of information that wasn't necessary to use, but it wasn't irrelevant in that there was another way that we could have done it using that information. I'm telling you this, in more than 80% of the regions, every detail in the problem is relevant, which means that you should not basically ever cross out any information calling it irrelevant. Okay? Basically never. Basically never. So on that note, numero 21, number 21, chemical reactions are most likely to occur when reacting particles collide with the proper energy and proper orientation. And I have this diagram here. Or proper first ionization energy and proper molecular symmetry, or same mass and same number of electrons, and same number of valence electrons and same number of electron shells. Okay, so chemical reactions are most likely to occur when the reaction particles collide with what? It helps to think of various reactions that you could make. Hydrogen and oxygen make water, for example. Carbon and oxygen make carbon dioxide. Sodium and chlorine make sodium chloride. So, but what happens? They have to collide, sure. So if they have to collide, proper energy, if they have the proper energy for the collision, that it can't be wrong. And the proper orientation, that one almost has to be right. So I'm liking this answer because if they have the proper energy for the reaction, great. And they have the proper orientation, that actually makes it even better, right? Now, the proper first ionization energy, what's wrong with that one? First, sometimes it's and proper molecular symmetry. So the first ionization energy, sometimes you need a different energy is needed. Worth noting, sometimes you don't have to ionize an atom or a molecule to create a reaction. And the proper molecular symmetry is not required. So it's not this one. Okay? Now the next one, the same mass. Why can't things with different masses react? Hydrogen and oxygen have very different masses, right? Hydrogen and carbon, very different masses. Polyatomic ions can have quite extreme masses. So that one should not be it. And the same number of electrons, while the atomic numbers can vary extremely. A 1 versus a 70, and the number and the atomic number corresponds to the number of electrons. and the sum of the atomic numbers corresponds to the sum of the number of electrons. So that would not be it either, the same number of electrons. Now the last one, the same number of valence electrons and the same number of electron shells. So now the same number of valence electrons, this actually is something that's very opposite of many reactions is true. Same number of valence electrons, in fact, usually better, it's better if the number of valence electrons in one chemical equals the number of electrons holes in other chemical. So the same number of valence electrons does not assist in a chemical reaction. That helps. This helps, especially in an ionic bond. But yes, they can have the same number of valence electrons sometimes. But it's definitely not required. Like HCl, definitely not required. As opposed to O2, yes, they have the same number of valence electrons, but then they form a covalent bond. So that's different. Then the same number of electron shells, not at all required. In fact, we learned that the elements in the same group tend to have similar chemical properties. But the same number of, if you go down the group, they have different number of electron shells. So definitely not true. The only one that has the correct one is this one. But before you switch to numero 22, number 22, if you want to fast forward to numero 22, number 22, sure, go ahead. But I'm giving you the gold over here. I'm making the goat of all Chemistry Regents videos here. So might as well hold on for just a second. This one says, and I'm going to expand it a little bit. Oh, I guess this image got attached to the letter somehow. There we go. You see, this one has NO, nitrous oxide, and O3, ozone, reacting, coming together to make an activated complex. This one, top one, met and collided with the ozone in such a way that the N collided with the O, corner O of the ozone. The bottom one collided such that the O in the nitrous oxide and the O in the corner O in the ozone collided. And notice that the reactants are the same. NO plus O3, NO plus O3. In other words, no reaction. And we know that they can react. So what happened? They collided with the correct energy, suppose it did, just the wrong arrangement. Whereas this one, this nitrogen collided with this oxygen, and the nitrogen stole the oxygen from the ozone to make nitrogen dioxide plus a free oxygen molecule. Not a free oxygen molecule, and the standard stable, nice stable O2 molecule. So yes, the energy and the orientation both matter to make an activated complex. By the way, generally speaking, the activated complex has more potential energy than the reactants, and then the products have less potential energy than the activated complex. Now, which one has more potential energy, the reactants or the products? Well, that actually depends on the reaction. We know that there's more entropy in the products, and it does happen to be that most chemical reactions, this is just statistically true, most chemical reactions that are one directional do tend to release energy. Some absorb energy. So we'll talk about that more, and there is a problem that actually asks that specifically, like 70 something. So we'll talk about it when we get there. Numero 22, number 22, at STP, a 2.0 liter sample of nitrogen gas and a 2.0 liter sample of oxygen gas have equal atomic masses, number of molecules, densities, or boiling points. Well, this is STP, 2-liter sample of nitrogen and a 2-liter sample of oxygen. That means that the oxygen and the nitrogen have the same container, and there's the same amount of each. The boiling point, therefore, is actually just determined by the chemical. So, and I do know that different chemicals have different boiling points. We're looking for equal. So I'm going to immediately cross out the one that says boiling points. Okay? Densities and atomic masses and a number of molecules might be looking okay, but if we think about, again, which ones have to be wrong or which ones have to be right, again, I recommend gravitating for, this is another test taking strategy, super gravitating towards determining what is wrong as opposed to what is right. Because in many problems, there's 10 to 50, without exaggerating, 10 to 50, maybe even 100 ways of doing the problem correctly. But when you unbound yourself to determining what is incorrect, there's often thousands, and that's, again, without exaggerating, thousands of different ways of determining which answer is incorrect. That, again, is without exaggerating. There may be thousands of ways of determining which one is incorrect. And if you think about what a sample of oxygen and another sample of nitrogen look like, if I go to my reference table and I think about the atomic mass of nitrogen around 14, the atomic mass of oxygen 16, well, that implies that N2 has an atomic mass of 28 and O2 has an atomic mass of 32. So the mass of a 2-liter sample of oxygen at STP has to have the mass of O2, it has to be greater than the mass of N2. So the atomic mass can't be the same. And because the atomic mass can't be the same, and I'm going to show you another reason why you could eliminate the density also. Since the atomic mass can't be the same, the density also has to be different. Again, because the volume is different, therefore the atomic mass, because the atomic mass is different, therefore the density has to be different. That actually is the reason why choice one, another reason why choice one and choice three could be eliminated. Again, if you free yourself to think why some problems why some answers could be eliminated, you may have thousands of ways of determining which one is incorrect. So choice one and choice three imply each other. Okay, remember that density is equal to mass over volume. Okay, density is equal to mass over volume. And if you don't believe me, the beauty is that there is a formula sheet in your reference table. Oops, went too far. What just happened there? Why is it like changing pages? There we go. The density formula is right here. Density equals mass over volume in the formula sheet. So if the density, we already know that the volume is the same. Same volume, 2-liter. Therefore, same density implies the same mass. Density is equal if and only if the mass is equal. Okay? Which means that they imply each other. Which means that if one is right, the other one would also be right. And since this is a multiple choice question, they can't both be right. Therefore, they're both wrong. And even if I didn't know how to eliminate one of those two, they eliminated each other. And now I'm left with choice two being incorrect. Isn't that beautiful? A nice test-taking strategy. Choice one and choice three implied each other. Here it is. Choice one and choice three implied each other. Since this is a multiple choice test, if choice one is true, then choice three is true, and they can't both be true. So if choice three is true, then choice one is true, and they can't both be true. They both eliminate each other, and therefore the only remaining answer is choice two. Beautiful. Número 23, number 23. Based on table H, which compound has the weakest intermolecular forces at 75 degrees Celsius? Before I look at this problem, I'm going to go to table H. Table H. There we go. Okay. Now, table H is like vapor pressures. And you might say, wait, intermolecular forces. And they just talked about vapor pressure in this chart. Let's get a screenshot of this and bring it into this test. Let's see, I might have to shrink this a little bit. There we go. So, yes, the full table is here. Okay. Which compound has the weakest intermolecular forces? And this is talking about vapor pressure. Vapor pressure. So, is it ethanoic acid, ethanol, propane, or water? Now, if fake student me is having trouble with this, I might say to myself, I see that in order, propanone, ethanol, water, and ethanoic acid are here. And I remember that water has really strong intermolecular forces because of the hydrogen bonds. And I am familiar with ethanol. That is rubbing alcohol. Actually, that's drinking alcohol. And sometimes it's in rubbing alcohols too, but it's drinking alcohol. So I think that the intermolecular forces of water are going to be higher than at least some of these. So, and they said the weakest. Okay. So even fake student me doesn't understand this chart, I might say that. Then test taking strategy says, well, if one of these has weaker intermolecular forces, I think that the middle answers can't be the answers. So I think that I'm actually going to cross out ethanol because the more extreme answers are on the outside. Propanone and ethanoic acid are on the outside of this chart. So test taking strategy me tells me I think those are not going to be the answers, and the answer is going to be either propanone or ethanoic acid. And now I might be stuck here, and I have to think about why one of these answers might be right or might be wrong. And I would not give up here. I would not give up here. Even if if you categorize yourself as a struggling student, I would not give up here. I remember asking which one has the weaker intermolecular forces and which ones have the stronger intermolecular forces is the same question. Just reversed, answer one, you answer the other. So focus on the one that makes more sense to you. Weakest versus strongest. And then I might say to myself, well, intuitively, if they have a stronger, if this is vapor pressure, oh, I'm saying to myself, well, if they have stronger intermolecular forces, then the bond in that molecule has to be strong enough to keep it like liquid for longer. And now I'm saying, oh, okay, so I see that ethanoic acid has a boiling point of like almost 120, 117.5. I see that there it is. Let me draw a better line than that. Okay. Not the best line, but sure, I'll take it. Water, I know its boiling point, 100 degrees Celsius. I see that ethanol has a boiling point just around, it's not going to straighten my line. Okay, that one's not going to straighten. Around 70, around 80. I know it's like 79 or something like that. And then propanone, sorry, has a boiling point around 55. So the one that has the strongest intermolecular forces is that one. Because it has the higher boiling point. In my intuition, the higher intermolecular forces keep the molecules together for longer until it finally gets to boiling. And then this one is the weakest. And that's actually it. The thing that keeps a liquid together is the intermolecular forces. And you might say, well, what about gravity? Well, it does turn out gravity does have the tiniest effect. You have to have quite large molecules before gravity actually has effect. And this is something that you should kind of know, that gravity as a force is far weaker than intermolecular forces. So the governing property for all of this, for a boiling point, is intermolecular forces. Okay, so the weakest intermolecular forces have to be propanone. So that has to be the answer. Okay, so we learned test taking strategy, and we learned how to determine the intermolecular force strength. That's sweet. Número 24, number 24. Which term identifies a force of attraction that exists between molecules of water? Between molecules of water. And we've talked about this one. Covalent bond, hydrogen bond, ionic bond, and metallic bond. And so I would eliminate metallic bond because water is not a metal. I would eliminate ionic bonds because water is not a salt. This is metals only. And ionic bonds is salts. But what about hydrogen bond or covalent bond? So here's the thing. This is where some students get it wrong because they didn't read the problem carefully. This covalent bond is between H and O in a single H2O molecule, whereas this hydrogen bond is between H and O in separate hydrogen and oxygen, or separate H2O molecules. We drew it earlier in the test. I'm not going to scroll to it, but remember, I'll draw it here. If you have an O, an H, and an H, this H, which has a positive charge on the left side, is attracted to an O, which has a negative charge on the top. And that is where the hydrogen bond occurs. That's a hydrogen bond right there. And they call it a bond because it actually is a very strong bond. And this bond is so strong that it actually persists for a measurable amount of time. It's not just a simple reaction, a simple attraction. So why do students get this wrong? Well, here's a hydrogen bond there, but here is a covalent bond. In fact, in yellow, I'm gonna highlight covalent bonds. Then I'm going to highlight the covalent bonds. And then the hydrogen bonds, I'm going to highlight in cyan. Then I'm going to highlight that spot right here in cyan. And there'll be another hydrogen bond up here. Okay. Between this top molecule of water with another H of another molecule of water. So yeah, so that's how you determine that's how you know that there's both kinds of bonds here. And then if you go to the problem, they said between molecules of water. Between molecules of water. Not inside of a single molecule of water, but between separate molecules of water. That is a hydrogen bond. Really easy to know that material really, really well and still accidentally get it wrong. Okay? And for number 25, number 25, I put a picture of this. You might say, what does this have to do with number 25? Numero 25. I'm sorry, no, number 26, number 26, but still. But number 25, numero 25, which process result in an increase in, actually both, sorry. Anyway, numero 25, number 25, which process result in an increase in disorder? The condensation of water vapor, the freezing of liquid ethanol, the sublimation of solid iodine, or the solidification of melted sodium chloride. Now let's see, condensation of water vapor, so this is gas to liquid. The freezing of liquid ethanol, this is liquid to solid. The sublimation of solid iodine, this is solid to gas. And the solidification of melted sodium chloride, this is liquid. Oops. Liquid to solid. Now look at this. Both 2 and 4 match each other. So 2 and 4 can't be the answer because they're the same. So test taking strategy says even if I thought the answer might be 2, that would imply that the answer is also 4. If I thought the answer was 4, that would imply that the answer is also 2. Can't be true, so they're both false. So now I have to compare what makes number 1 and number 3 different. Gas to liquid versus solid to gas. And then I actually compare gas to liquid has a similar property as liquid to solid. So fake student me is suspecting that this one is wrong. Solid to gas has the opposite property of all 3 of these. So I'm liking choice 3. Notice I put an X next to choice 1 as opposed to crossing out completely choice 2 and choice 4, because choice 2 and choice 4 I've confirmed that they're wrong. Choice 1 I suspect is wrong. Fake student me does, and choice 3 I suspect is right. So I put a check marks there. So if I suspect the answer is wrong, I put an X on the right of it. If I know the answer is wrong, I cross out the answer. If I suspect the answer is right, I put a checkbox next to it. If I know the answer is right, I circle it. Okay, so disorder, increase in disorder. I think about a solid, and the atoms or molecules in a solid are in very fixed places. Often they're in fact in very fixed and organized places. Crystalline solids, for example, are extremely organized. Whereas a gas, the atoms can go anywhere and fill a container. That is an extreme amount of disorder. Increase in disorder is what we're looking for. That's got to be choice 3. Choice 3 makes sense. Choice 1. Now, what about gas to liquid? Again, the gas can freely roam everywhere in the container, whereas a liquid is settled at the bottom. It's limited in how much freedom it has. In fact, that change from liquid to gas is what it literally is a gain in a degree of freedom, the freedom of movement in any direction. The reason that a gas, a liquid changing into gas doesn't change in temperature initially until you keep heating it, is that the entirety of the energy that is absorbed in the phase change is absorbed in receiving that degree of freedom. In other words, it gained potential energy. So the entirety of that phase change energy is absorbed to create potential energy, not kinetic energy. And heat is temperature is a measure of the average kinetic energy. Okay, now número 26, and I said that number 26, número 26, and 25, número 25 will have something to do with this. It says systems in nature tend to undergo changes that result in an increase in both energy and entropy, a decrease in both energy and entropy, or an increase in energy and a decrease in entropy, or a decrease in energy and an increase in entropy. Okay, this is important to know. Systems in real life increase in entropy, always. Okay. Now you might say, oh, but if I have a closed system where I change something from liquid to solid, like I did in choice 25, liquid to solid or gas to liquid, I just reduced entropy. Yes, but in real life, there is no such thing as a perfectly closed system. In fact, when you change the phase from liquid to solid, so that released energy, where did the energy go if the temperature didn't go up? It releases it as radiation. So it releases it out of the system. So there is literally no such thing as a closed system. Yeah, systems in real life go towards an increase in entropy. So any that have, and that's an important one to know, increase in entropy, systems in nature tend to undergo changes that result in an increase in entropy. So we want increase in entropy and not a decrease in entropy. So decrease in entropy, increase in entropy. So now we have a choice 2 and choice 3 are incorrect, and we have a 2 by 2 problem. Okay, so systems in nature, what do? They tend to, do they then tend to increase in energy, or do they tend to decrease in energy? Do they tend to increase in energy, or do they tend to decrease in energy? Well, um, if systems in nature tended to increase in energy, they would literally just get hotter in nature, and hotter and hotter and hotter. And everyone who's ever held a cup of coffee knows that that coffee doesn't tend to just get hotter and hotter and hotter and hotter. In fact, energy travels from an area of high energy to an area of low energy, or in other words, from a hotter to colder. So the thing that's hotter tends to get colder. In fact, if you completely try to isolate something that is hot, let's say you put it in the middle of outer space, surrounded by nothing, it'll literally just radiate its energy um, through black body radiation. Things tend to things tend to decrease in energy in real life. So a decrease in energy is what tends to happen in real life. And the reason I put this picture here is, if you notice, the dock did not build itself. The dock, in fact, was decomposed by the water. That is a very extreme increase in disorder. Okay? Increase in disorder. And disorder is another word in chemistry class for entropy. Okay? But now the pieces of this dock, right, fell to the water, right? They fell. The pieces over here, big pieces maybe, fell, and pieces broke, and by breaking, they release energy too. By falling, though, that is going from a place of higher energy, falling to a place of lower energy. So it's also a decrease in energy. Okay? It's a great example. Docks don't build themselves, so entropy does not tend to increase. And on that note, we're going to go to número 27, number 27. Okay? What is the general formula for the homologous series that includes ethine? Ethine. Okay? Is it CnHn or CnH2n or CnH2n minus 2 or CnH2n? I'm sorry. Let me reread these. Ethine. So is it CnHn or CnH2n or CnH2n plus 2 or CnH2n minus 2? And so, believe it or not, though, this is in the reference table. Okay? So if you look at table Q, the answer, this is rare, but the answer, and this is not the only one on this test. This is rare, but the answer is just there. Where is it? Literally there. And look at the structure of ethine. So these are alkynes, ethines. They could have called it propyne. Like they could have just literally given you, or like some other variation. They would have to say more than just propyne. But they literally just gave you the answer, reading it. So it's almost, even though it's problem 27, which later on in the test it should be a little bit harder of a problem, they literally just straight up gave us the answer, choice 4. So no process of elimination there. Literally a reference table problem. Okay. Número 28, number 28. Given the equation representing the reaction, 2Ki plus F2 reacts to form 2Kf plus I2. When 2 moles of electrons are gained by fluorine, how many moles of electrons are lost by iodine? This one is, I think I could imagine why it might be a little bit tougher, but there is just a numerical statement that you can make here. So 2 moles of fluorine, of electrons are gained by fluorine. How many moles of electrons are lost by iodine? So it can't be 3 because of the numbers here. Just the numbers, you either have the same number, right? Or because there's ones and twos there, it has to be 1 or 4. 1, 2, or 4, in other words. 1, 2, or 4, in other words. There's no way to get a 3 because that would be imply that 1 mole of if 1 mole of electrons are gained by fluorine, then somehow 1.5 moles of electrons are gained by iodine. In practice, that is possible in different when the indices are not multiples of 2 and the coefficients are not multiples of 2. But in this case, the indices and the coefficients are all multiples of 2. So it's either 1, 2, or 4, not 3. 3 is not physically possible. So how did I do this? I had to, this one might be a little tougher because if you're not used to splitting up the chemical reaction into its component parts, but that's how I ended up doing this one. And there is another question that actually asks us to break up the reaction into component parts. So I'm going to show you how to break this reaction into component parts. So you have Ki. If you go to the reference table, potassium is a group 1 element. Okay. Again, in the reference table here. K, potassium is a group 1 element. And group iodine is a group, let me rotate this so we can see it. Potassium is a group 1 element, so it has 1 valence electron. Iodine is a group 17 element, so it can gain 1 electron. So this is 2K. Now the K releases an electron, or the K started as having released an electron, and the iodine started having gained an electron, plus the 2 irons. F2 is 2 individual irons with 0 electrons lost to each other. They're both sharing in common a single electron. These react to form 2 potassium. Now the potassium once again loses an electron to the fluorine, plus the fluorines gained an electron. I'm going to put -1 for this, -1, plus the iodine. 2 individual iodine atoms have 0 electrons. So notice here, they said how many electrons, if 2 moles of electrons are gained by fluorine, and there's 2 moles of electrons. So each mole gained of fluorine gained 1 electron. Okay? And each, if you look over here also, so that's, let me highlight that in here, 2 moles gained 1 electron. Okay? And then the same thing happens with the iodine, except the other way around. Each mole of iodine went from -1, which already had an extra electron, went to 0 electrons. And there's 2 of them. I'm regretting highlighting the way I did. How am I going to highlight? Each mole of fluorine gained 1 electron. Each mole of iodine lost 2 electrons. Okay? And so we have 2 times 1 equals 2 gained by fluorine. And then each mole of iodine lost 1 electron. And we started with 2 individual moles of iodine separately. So 2 times 1, each mole lost an electron is equal to 2. So these are called, individually, they're called half reactions. If you split them up, half reactions into electron gains and electron losses. If you split them up, electron gains and electron losses. So why did I have to do it that way? Because I actually had to determine that the potassium didn't gain or lose electrons. If the potassium gained or lost electrons, then that would change the answer. That said, número 29, number 29, which compounds is an Arrhenius base? An Arrhenius base, is it H2SO4? Or is it NaCl? Or is it CaOH2? Or KNO3? Now, CaOH2 is looking mighty fine to me, because I know that bases tend to have OH ions. It's looking mighty fine to me. So this one's looking mighty fine to me. The other ones are not looking good to me. In fact, this one is an acid. Sulfuric acid, right? So it can't be that one. This is salt. This is table salt. So it's neutral. And so I'm stuck with KNO3. So I have a 2x2 problem already. So this is neutral, okay? I have a 2x2 problem, and I'm liking CaOH2. So even if I don't know what an Arrhenius base is, I'm really gravitating towards choice 3. So what is, let's actually define what an Arrhenius base is. An Arrhenius base, it is a chemical which increases the concentration of what bases tend to do, of the OH minus ion, of the hydroxide ion. So which one of these chemicals does that? Well, the CaOH2 definitely does that. How can I know that? There is a table of ionic compounds. Let's see, ionic compounds. Compounds with hydroxide ions, they actually tend to be insoluble, except for in the cases when they combined with group 1 ions, or if they're like, for example, Na, right? NaOH, that's NaOH, that's a base. Sodium hydroxide, forgot the name for a second. Sodium hydroxide. I remembered the name sodium, but I couldn't remember the name of the base, but sodium hydroxide. But these tend to be insoluble, and the exceptions are when they're combined with group 1 ions like sodium, or with these really very specific ions, including Ca plus 2. So those are soluble. If they're soluble, they're going to release tons of OH ions. So it is there. So that's, where's that table? Again, table F. So this is part of table F, okay? And then so KNO3 is not the answer. Let's go to number 30, number 30. And I have this nice nifty picture there. Most of the nifty picture is actually just artistic. I believe that most of the picture is artistic. You see this like fractally looking cool stuff? Sure. But for a moment, let's ignore the fractally cool stuff. There is a bunch of gray and red particles in a tight bunch, and this is a nucleus, okay? And so what is the red? The red is equal to a proton. Now keep in mind, these are bunches, and they have to be visible, so they're not going to draw the exact right number of protons. But the gray, or the black, is equal to a neutron. Okay? Now, I noticed that these two big nuclei just split in half, and they released a neutron going really fast in that direction, right? And then a neutron here going really fast in this direction, right towards this nucleus, right? And then there is usually, depending on what fission product, what fissionable element this is, there might be another one that was maybe released in this direction. Because in most reactions that you care about, there's 3 released, but it does have to be, generally speaking, more than one for fission to be self-sustaining or to be able to go out of control and create, for example, a bomb. So this neutron, this big nucleus split into two, well, split into multiple parts, but split into 2 new nuclei that are smaller, but also spits out a few neutrons. Now, one of the neutrons or more collides into another nucleus of one of those bigger atoms. And what happens is once this one gets in here, it creates a fissile element, which then causes this nucleus to split up into a bunch of reds and blacks again, with three more neutrons, and maybe one of these neutrons goes to hit another nucleus and causes that one to fizz as well. So all the fractal stuff, I don't actually know whether it actually represents anything. It was just a cool image that I found that I think makes it a bit clear. So this is fission. Now, which statement best describes a benefit of fission? Número 30, number 30. Which statement best describes a benefit of fission? Fission produces nuclear power. True. It does do that. Fission increases the possibility of nuclear accident. This is true. But they said benefit. Not a benefit. Right? Increases the possibility of biological exposure. Not a benefit. Right? We're not Spider-Man here. Or fission produces waste products that need long-term storage. This is not a benefit. A lot of students do get this question wrong, despite the fact that there aren't any benefits, because they look at what is true and they stop there. And then they didn't go back to the problem and reread it. Let me just be clear with you here. It is normal to read a problem more than once. It's in fact expected to read a problem more than once. You want to know what the really nerdy kid like me, by the way, nerd is a compliment. So if you hear me call somebody nerdy, nerd is a compliment. You want to know what those nerdy kids do to do better on the tests? They read the problems on average up to 5 times. That's literally the average. So if you, as a struggling student, are reading the problem less than 5 times, you are actually making an active mistake. You should be reading it up to 5 times. Now, granted, can you read it more than 5 times? Well, after more than 5 times, you might get more out of it than the nerdy kid might have, because you might struggle and you might need more than 5 readings. But at the same time, now you have to do time management. But if you've only read it once and you tried to answer it then, you've actually just made a mistake, a strategic mistake. You're supposed to read it more than once. I'm doing the problem and I'm reading it more than once to make sure that I did it right. And I actually confess that I actually got some of the problems while I was doing it partially incorrect, or I struggled with them because I just misread them. Literally. So if I can misread them, so can you. And if I'm a teacher and I can get 100 on this Regents, maybe if you get 80s, maybe you should be rereading the problems way more than once. And again, taking that advice, the problems tend to have 0 irrelevant information. All right, so B1, all the parts of the chemistry exam are basically the same. So the differences between all the parts don't really matter. We still need the reference table. These are still multiple choice questions, and eventually multiple choices are just going to stop. Sure. Número 31, number 31. The number of protons, neutrons, and electrons in each of 4 different ions are shown in the table below. So I do read the table briefly, and then I move on and then go back to the table. So I read ion AEGZ, number of protons 49, 50, 50, 51. Just take that in, let that process the way it processes, but I'm not consciously processing it. Number of neutrons 60, 70, 69, 59, and number of electrons 46, 48, 46, 48, 48. Okay, let that just sit. Which ion has the greatest mass? A, E, G, or Z? A, E, G, or Z? So greatest mass. The mass number. The mass number tends to be equal. The mass number is equal to the number of protons plus the number of neutrons, and it tends to be almost exactly equal to the atomic mass. Now, you might say, why is the atomic mass and the mass number slightly different? There's actually two reasons. One, the nucleons to bind together, energy has to be released. Okay, and that's true for virtually every nucleus that matters. Definitely for every nucleus under lead. Okay, so energy has to be released in order to form the nucleus. Um, now, so that's one reason why the atomic mass might actually be slightly smaller. But the other reason is that the atomic mass, when you look at it in the reference table in the periodic table, the atomic mass is not just a function of how many protons and neutrons it is, but it's also a function, at least when we give it to you, it's a function of the prevalence of each isotope on Earth. So sometimes one isotope that's lighter has some sort of prevalence. Sometimes an isotope with more neutrons has some prevalence, and so then the atomic mass that's given in the reference table might vary slightly. And why does that matter? Because when we do chemical reactions, we take our chemicals from nature. If you were to do chemistry on an asteroid, let's say 100 years from now, when we start landing, or maybe 20 or 30 years from now when we start landing on asteroids, you might have a slightly different reference table because the ratios are slightly different. Okay, so the mass number is equal to the number of protons plus the number of neutrons. Notice I didn't include the number of electrons because the electron mass is like 1,000th, less than 1,000th the mass of a proton, and even slightly less than the mass of a neutron. So that means that the mass number is not really affected by the mass of a neutron, and we actually by the mass of an electron, and we ignore it. So the mass number is equal to, we have to look for the greatest mass. We have to add the number of protons plus the number of neutrons. We do 49 plus 60. Use your calculator. It's 109. We do 50 plus 70 is equal to 120. We do 50 plus 69, which is equal to 119. Now, even if I didn't know how to add or struggled with adding, I would eliminate this one because this one has the same number of protons but one less neutron, which makes it lighter even before I do the arithmetic. And then 51 plus 59 is 110. 51 plus 59 is equal to 110. Okay, so the one that's heaviest is Número 32, number 32. The mass of a sample of nickel is determined to be 20.40 grams. How many significant figures are used to express this mass? 1, 2, 3, or 4. So there's an acronym I like to use. NAD. NAD. Sometimes I used to use NAS, NAS, NAD, or you could do NADS. It's kind of a funny acronym, so we'll keep it. But the N stands for never. The A stands for always. And the S stands for sometimes, right? But now, that's what it stands for sometimes. It stands for sometimes, but the D stands for decimal. So wait, never always in decimal. So what are these even referring to? Okay, so here's and I'm teaching it this way because I know teachers teach it and we still struggle with it going into the regions. Now I have to explain it to you one time in a way that sticks to you for the regions. So NAD is the way I make it stick to you. So this is something that, and by the way, that I do when I tutor. when I tutor, I only, like, unlike teaching something to you, when I have to repeat it a certain number of times and a certain number of students get it, and that's what the goal, I have to actually explain it to you in a way, one time only, in a way that sticks to you until the Regents. So NADS is going to stick to you until the Regents. Here's what is true. First off, every non-zero digit is significant. Okay, so which digits are, let me scroll up a little bit so we can see it all, significant. Okay, every digit is significant. And then what about zeros? Zeros follow the NAD rule. The NAD rule. NAD rule. So I want this to stick to you. What is the NAD rule? Okay, leading zeros, zeros in front at the beginning of a number. Zeros, so leading zeros are never significant. Never significant. Leading zeros are never significant. So like 0.0050360 000. Okay, not significant. Never significant. Okay, the second step, middle zeros. Oops, meant to do that in red. Middle zeros are always significant. So middle zeros, like that one right there. There aren't any ends, right? The leading zeros, no leading zeros, never significant. That middle zero right there, always significant. And then finally, the ending zero, this is the ending zero. D, this is the D. Ending zeros. Now, I used to say S for sometimes, but then students forgot it. And then I used to use D for decimal, and then students forgot it. So I use NADS because it's only sometimes when there's only a decimal. So ending zeros are only significant. So decimal significant. Decimal, so ending zeros are only significant if there is a decimal. Okay, ending zeros are only significant if there is a decimal. So DS, decimal, implies significant. Okay, so this number that I put in, and sorry, I have to scroll the rule. Again, ending zeros are only significant if there is a decimal. Decimal significant, NADS, decimal significant. So this one I wrote here has a decimal. It has a decimal. So they're significant. So this number has how many significant figures? 1, 2, 3, 4, 5, 6, 7, 8. 8 significant digits. The leading zeros were never significant. All the non-zero numbers are significant. So 5036, 5, the 3, the 6, they're got to be significant. And then the leading zeros, never significant. The middle zeros are always significant, and then the ending zeros are only significant if there's a decimal. Decimal, significant, NADS, okay? So I want that NADS rule to stick to you. So same thing with this one. This one, so we got 1 and 2, and then the 4 is significant, and then decimal makes that 0 significant, 4. So this one has 4 zeros. Now, can we come up with an example that doesn't have a 0 that's significant? Sure. How about the number, let's say the number 50, like the number of views, no, that's not a good example. The number of page, my weight, I weigh 210 pounds. So every non-zero digit is significant. And then so the first 2 is significant. The 1 is significant. But what about this 1, the 0? So first of all, leading zeros are never significant, and there aren't any. Middle zeros are always significant, but there aren't any. And then the leading zeros, the ending zeros, decimal implies no decimal implies not significant. So this number only has 2 significant figures. Now, can I make the 210 have a 3 that is significant? I'm sorry. Can I make the 210 have a 0 that is significant? Sure. 210 point LB. Look at this. Leading zeros. Well, first off, this is significant. The second is significant. The leading zeros are never significant. The middle zeros, which there are none, but they are always significant. So 0 and 0. And then the ending zeros with a decimal, yes, there's a decimal, I put it there, implies significant. There's 1 ending 0. So third. Can I make a 210 have 4 significant digits? 210.0. Leading zeros. So first off, this is significant. This is significant. Leading zeros, never significant, but there aren't any. Middle zeros are always significant, but there aren't any. Well, leading zeros are never significant, so they're always not significant. But leading zeros, so I'm not even going to put the 0 on top, actually. About the notation here. That's a little improvement on my notation. And then the decimal zeros, they're significant, and there's 2 of them. 3. So there's a total of 4 significant digits. And this one has 3. And now we know how significant figures work. Let the NAD stick to you, and you can get the significant digits problems right. Número 33, number 33. What is a chemical name for the compound PbO2? So first off, Pb is, according to my reference table, right? According to my reference table, Pb is lead. So we do want to know that one. Let me see. According to my reference table, Pb, let's rotate this real quick. Pb is lead. Where's lead? Did I not go far enough? Lead. You know what? Maybe I should check the reference table for the atomic number because I blanked on the atomic number. Pb. And now I just blanked. Literally had it a second ago. There we go. 82. The moment I saw the D, the P and the D mixed. So Pb, if I forget what Pb is, then Pb is lead. Now it does turn out we didn't need it so much because they all have lead in it, and then they all have oxygen in it. So Is it lead 1 oxide or lead 2 oxide or lead 3 oxide or lead 4 oxide? This is literally testing. Do you know what this Roman numeral means? And I didn't learn what the Roman numeral meant until my second year of chemistry. In my school, we had actually 3 years of chemistry, and I didn't learn what the Roman numeral meant until my third year of chemistry. So if you don't know, that's okay. But now you get to learn it. The Roman numeral equals the number of electrons donated to the oxygen. Let's say not donated to the oxygen, because it doesn't have to be oxygen in another problem. Donated in the reaction. So now, how do I determine this? Well, oxygen has 6 valence electrons, and it wants to get 2 more from the lead. And it's PbO2, so there's another oxygen right on the side with 6 valence electrons. And it wants to get 2 more also. So the lead donates 2 to this oxygen and donates 2 to this oxygen. And then finally it has 4 more, 2 on top and 2 on bottom. So how many electrons did the lead donate? 2 plus 2 equals 4, which is equal to the Roman numeral IV. So this is lead 4 oxide. By the way, if I were doing this a multiple choice, I don't even like the 3. There's nothing in the problem that would lead me towards a 3. Like if I was fake student me, I'd just cross out the 3 in this case, because I can't imagine how a 3 would come into the problem, given that I have 2 oxygens and a lead. I don't know. That's like fake student me not knowing how to do this problem at all. But real student me does know that the Roman numeral represents how many electrons that the lead is donating in the balanced reaction, and the lead is donating 4 electrons in the balanced reaction. Therefore, it's lead 4 oxide. Okay. Número 34, number 34. Which formula is the empirical formula for ethane? C2H6. And this is, again, the empirical formula was the one that we were talking about earlier, and I said that it would come up again later. C2H6, we have to divide by the GCD of 2 and 6. I know this is a math problem, but to the GCD of 2 and 6 is equal to 2. 2 divided by 2 is equal to 1, and 6 divided by 2 is equal to 3. So the empirical formula is equal to, and I know that we do not write 1s, but it would be C1H3, but we don't write the 1, so it'd be CH3. Okay? If I didn't know how to do this problem, I would cross out number 4 immediately. But if I didn't know how to do this problem at all, then I'd kind of be stuck at that point. But it is that this is how you do it. You literally divide by the greatest common divisor of all the indices. And so the answer is 34. But again, a strategy process of elimination, you might say that eliminating one answer is not even, doesn't help. But having a 1 in 4 chance of getting it right versus having a 1 in 3 chance of getting it right. If you have literally 20 problems on the let's do a nice multiple. If you have 24 problems on the test that you have no clue how to do, if you wild guess on 24 problems, 24 divided by 4, well, that's equal to 6 problems correct. This is wild guess. 24 out of 4 out of 24 problems you wild guess. 24 out of 4 problems is 6 problems. Okay, you do get on average 6 problems correct. It's not 0 that you wild guess on and you get 0 correct. It's actually on average 6. It might be a little more than 6, might be a little less than 6. Okay, but here's a guess after eliminating one choice. Well, in this case, if you've eliminated one choice, then out of 24 questions, you've eliminated one choice. That means you could divide the number of questions by 3 instead of 4, because there's not 1 out of 4 chance of getting it right. There's a 1 in 3 chance of getting it right. And 24 divided by 6 is 8 problems right. I said 8 problems right, and I wrote the number 6. Okay, 8 problems correct. So wild guess, 24 out of 4, you get 6 problems correct. But guess after eliminating one choice, 24 divided by 3, you get 8 problems correct. Even better than that, though. If you use other strategies, it's almost a guarantee that out of the 16 problems that you would have gotten incorrect after you just kind of guessed, you probably increase that number by a whole lot. Because once you eliminate one choice for being, let's say, obviously incorrect, hopefully one of the choices is obviously incorrect, then the other answers, you might be able to eliminate them for other correct reasons. Now, notice that in this test, I am actually gravitating towards eliminating answer choices for true, correct reasons. I don't really go for, oh, I think this is true, or I think that is true. I actually eliminate choices based on what I know is true. And I actually don't go towards what I think is true until way later, way later. So generally speaking, like for example, something doesn't jive right because it doesn't quite make sense. Again, 10 to 50 ways of getting the problem right, but literal thousands of ways of eliminating wrong answers. Okay, on that point, number 35, number 35, given a balanced equation representing a reaction 2CO gas plus O2 gas reacts to form 2CO2 gas plus energy. Which mass of O2 reacts completely with 5.6 grams of CO gas to produce 8.8 grams of CO2? So this says that it reacts completely, which is doing you a favor. 5.6 grams of CO. And then 8.8 grams of CO2. Do you remember that I said that there's never any irrelevant information? This problem also doesn't have really truly irrelevant information. Just like in a math class, technically it's not relevant whether you're buying cantaloupes or cans of soda or candy. Like, that's technically irrelevant, but we don't care about that. We still use it. In this problem, it doesn't matter that we're producing energy. The amount of energy in chemical reactions is so low that it has basically zero effect on the mass. Using Einstein's law, E equals mc squared, the mass loss due to energy loss to the environment is so negligible that for an extremely long time, physicists didn't even know that it was real. So it was Einstein that came up. I think it was Einstein who came up with the equation E equals mc squared. They give him credit for it. So in every video that I see, so I'm pretty sure. Although there's some things that they say he did, but there's actually someone else who did it before him. Anyway, point is, you can use complex methods of like finding out what mass of carbon you have, what mass of oxygen you have in CO, the 2 moles of the 2 CO, and then find out what mass of carbon you have in the products and what mass of oxygen you have in the products, and subtract that to get the mass of O2. So technically, all that reaction is not irrelevant. However, there's the law of conservation of mass, which provides a much easier way of doing this problem. So the starting mass is equal to the ending mass. Now, about process of elimination, remember I said if you could eliminate one choice, that is worth your time. How much mass of oxygen reacts completely with the carbon monoxide, 5.6 grams of carbon monoxide to produce 8.8 grams of carbon dioxide? it has to be the mass. The mass has to be less than 8.8 grams because you can't react a ton of oxygen and somehow make carbon dioxide that weighs less than the oxygen that you started with, which actually eliminates choice 4. You have a 1 in 3 chance of getting this right. Worth your time. But if you use the law of conservation of mass, I just wanted to make sure that I gave you some strategies to do process of elimination. Okay, but again, law of conservation of mass means that the starting mass is equal to the ending mass. So if you use the law of conservation of mass, let's call this X. 5.6 plus a missing mass is equal to 8.8. I'm going to not use an X because I'm a fan of using topically relevant variables. How about an M? 5.6 plus M is equal to 8.8. Subtract the 5.6, subtract the 5.6, and we get that the mass, using your calculator, or if they don't give you the calculator, which they're required to, but if they don't, 5.6 plus 3 is 8.6, and you need 0.2 more grams to get to the 8.8 grams. So the answer has to be 3.2 grams. Okay. 2.8 grams, I believe, is there for students who make an arithmetic error without using a calculator. And 1.6 is there because the individual atoms of oxygen separated. You have 1.6 grams of oxygen, another 1.6 grams of oxygen, but that's not what reacts with carbon dioxide. It's the O2 that reacts. And if you do separate the oxygens, you still have 3.2 grams of oxygen, just separated into 2 piles of 1.6 grams each. But that's not what's happening here. Okay, número 36, number 36. Which numerical setup can be used to calculate the formula mass of C9H11NO2? Numerical setup can be used to calculate the formula mass for C9H11NO2. Is it 9U plus 11U plus 1U plus 2U, or 12U plus 1U plus 14U plus 16U, or 9 times 6U plus 11 times 1U plus 1 times 7U plus 2 times 8U, or 9 times 12U plus 11 times 1U plus 1 times 14U plus 2 times 16U. Okay, I invite you to really think about this. The formula mass. It's quite a large molecule, C9H11NO2. Why do I make a note about the fact that it's such a large molecule? Because if it's such a large molecule, its mass has got to be a pretty big number. This is equal to 23. 9 carbons is heavier than 23. Has a bigger formula mass by itself than 23. 9 carbons has a formula mass that's quite big. This is not it. 12 plus 1 plus 14 plus 16, that's 30, plus 12 is 42, plus 4 equals 43. Again, carbon has a formula mass of 12 by itself. 9 carbons has a formula mass way bigger than 43 by itself, and not to mention the rest of the molecule. So this number is just too small. So even if I didn't know how to do this one, I have that information. Okay? Okay, let me do a quick look in the reference table. I just want to make sure. Yes. Okay. Nope. Okay. So that U is equal to the mass number. Okay. Let me see if I made a note of it. I thought that was somewhere in the reference table, but I just looked in my reference table. I just looked in my reference table for the U, and I didn't see it. Rotate this. So if you know, oh, here it is. There we go. Atomic mass unit, table D. Okay, so table D. U is equal to atomic mass unit. Okay, so we have C. The atomic mass unit is 6 plus 6 is 12. AMU. When I was young, we used to write just AMU. in our papers, but you know, things change, notations change. And how do I know it's 12? Actually, that's from this lovely, lovely table, 12.011. To get the atomic mass unit of each element, you literally just round this number. And almost all of these numbers round extremely close are extremely close, and therefore round more obviously to a nice integer. 1.001794, 1. 6.99, that's a 7. 9.01, right? 22.98. And then this one's a little bit farther. That has to do, again, that has to do with prevalence of isotopes. So the vast majority of them are just going to give you the number. But what you do is, again, what I just said, you literally just round the atomic mass to the nearest integer. Okay, so 12U, and then H, the atomic mass is 1U, N, the atomic mass is 14U, and O, the atomic mass is 16U. So then the answer to this is 9 times 12U, which is, this is already looking good, okay, plus 11 times 1U, that's great, looking great, plus 1 times 14U, which makes this one looks good, and that one again looks bad, and then plus 2 times 16U. And so the last one looks great, and this one just looks terrible. And so the answer has to be choice 4. All right, número 37, number 37. And if you feel like this video has been helping you, again, I do appreciate the subscribes. That's what actually makes me be able to keep this video free. Okay. I'm going to move that up here though, because I do need a screenshot of table F. Table F. Let me rotate this again. Table F. Which is most soluble in water. So we'll read this again. Okay. So based on table F, número 37, number 37, based on table F, which compound is most soluble in water? Calcium bromide, lead 2 sulfate, silver carbonate, or tin 2 hydroxide? Here's the thing. This table only said soluble or insoluble. So chances are we're just going to find some 3 insoluble compounds and 1 soluble compound. Let's see. Calcium bromide. So where is either calcium or bromide? So if we look for calcium or bromide, here's a bromide, okay? Here's a bromide, the halides bromide, form soluble compounds, and the exceptions, not soluble when combined with silver, lead, or silver. So Hg2 plus 2. So doesn't include calcium. So Ca, okay. Ca is okay. Let me write that. Calcium is not an exception. So this is looking good. So this is already looking good. So it's probably going to be that one. So now let's look for lead 2 sulfate. Lead 2 sulfate. We either have to find lead or sulfate. Okay. Let's see. Group 1 ions. Nope. Well. Oh, there we go. Sulfates. Sulfates are soluble, except exceptions when combined with silver, calcium, strontium, barium, or lead. Lead not dissolved. Lead plus 2. Lead 2, not dissolvable, not soluble. And then silver carbonate. So we have to find either silver or carbonate. There's carbonate. Insoluble with the exception of when combined with group 1 ions, which doesn't include silver. Silver is one of the middle group elements. Here's silver, group 11. Okay, so carbonate except when combined with group 1 ions, or ammonium, doesn't include silver, still insoluble. Probably insoluble. I mean, yeah, that's the best. I mean, this can't, it maybe isn't all the exceptions, but at least they put those in there. So we can only go by what they have for us based on table F. Remember, they're saying based on this table, so that's the best we could do. Now, tin 2 hydroxide. So now there's a hydroxide here. Are insoluble, and except the exceptions are group 1 ions, which tin is not. Group 1 ion again. It's not calcium plus 2. It's not barium. It's not strontium, and it's not ammonium. Again, insoluble. At least according to F. I mean, it's not on the list. So the best choice is a more obvious choice 1. It's right on the list, and it's at the end of the list. Well, we actually labeled it. So that's good. So I taught you how to use table F. If you feel like that was helpful, please let me know with a comment. The likes do help. The subscribes, obviously. I'm doing this for the subs because I want to see if this part of my business can actually improve my income. I do know I have gotten many clients through tutoring. So again, JuanTutors.com if you're interested in getting tutoring in math or physics especially, but also chemistry. I wouldn't be tutoring you in the English or history, but I do have tutors who tutor in that as well. So JuanTutors.com for that. Number 38. Based on table G now, which combination of solute and solvent will form a saturated solution when thoroughly mixed at 20 degrees Celsius? Now we got to go to table G. Table G. Okay. Let's get this a little bit smaller. So we have to get it. We have to. They say based on the table, so I think that this is definitely just a table reading. I think I have seen students kind of really overthink this one. Get this question wrong for just the wrong reasons. Which combination of solute and solvent will form a saturated solution when thoroughly mixed at 20 degrees Celsius? So if I look at the chart, this is temperature and solubility, and it has 20 degrees Celsius on the chart. So I need to look at 20 degrees Celsius. I mean, for my colorblind friends, I will use a blue. See if it straightens that number out. Perfect. 20 degrees Celsius. I'm looking at that blue line. So that's the 20-degree mark. So I'm going to do 3 or 4 different ones. Let's see, KClO3, here's this one, pointing to this line. Now you got to look at this graph carefully because I did get caught. This is another one I got caught. I looked at the wrong line. I followed the line down, and we are here. The maximum that water can dissolve, the maximum amount of KClO3 that water can dissolve is 9 grams, and 15 of KClO3. 15 is just greater than 9. So I suspect that this is it. Remember, saturated. So how can a solution be saturated? You might see, like you might think maybe you could just add more salt, and just keep dissolving it. Well, clearly at some point you're going to get a nice slurry of salt. And then eventually you're just going to have some wet salt. And eventually you're just going to have so much more salt than water that the water might not even be visible. So clearly water can't dissolve an infinite amount of salt, right? You can't take a cup of water, 100 grams of water, a tenth of a liter of water, go to a salt flat and dissolve all the salt with that water, right? So clearly the amount of salt that is dissolvable in the water is not infinite. But So it varies for different chemicals. And for KClO3, the maximum you could dissolve is 9 grams. And what would happen with the remaining amount if you added more than 9 grams? Well, it wouldn't dissolve. It would settle usually at the bottom. If the density happens to be low, then maybe it'll float to the top. But usually the density is higher, so it'll settle at the bottom. And it'll literally never dissolve. It'll just stay undissolved. What about the second one? Let's just make sure. So the one that I would normally eliminate is this one, because like the third one, I'll address the third one first, because I happen to know that table salt, NaCl, is actually highly soluble in water. And I look for KCl, NaCl right here, pointing at this one, and that's like right there, 38 grams. And I know that 30 is less than 38. And so it's not number 3. So this is just me making sure that I'm doing this right. If I'm failing if my intuition is failing me, maybe my definitions are failing me. Maybe like I didn't know what a saturated solution was. Then I can compare these numbers, and whichever is the odd one out has to be the answer. So I know that 30 is less than 38. So therefore, this solution is not saturated. I could add another 8 grams of NaCl and it'll still dissolve in water. 9 grams, though, 8 of the grams will dissolve in the water. The 9th gram will just settle to the bottom. The third one, I'm going to do this in this funky color over here. The second one, rather, 20 grams of KCl and 100 grams of water. Luckily, it's all 100 grams of water. And here's 100 grams of water. KCl, where's KCl? KCl. I had KCl. Now I'm going to go down this hill following. Again, don't get fooled by the line, because I got fooled not noticing the arrow in which way it was pointing. But now I got it. So I see that that's about 32. And 35 is just less than, I'm sorry, 20 is less than 32. So the odd man out is starting to be choice 1. And then finally, what pen remains? The black. Okay. And finally, the potassium iodide, Ki. Where's Ki? Ki is all the way up here. Wow. Tons of potassium iodide can dissolve in 100 grams of water. More potassium iodide. Wow, that's amazing. So you could just keep adding potassium iodide for a long while. And 35 is less than, what, 140, 145? So the odd man out is definitely choice 1, and that leaves choice 1 as the final answer. All right. Número 39, number 39, a solution has a mass of 2,000 point grams. By the way, remember what I said, significant figures. That has a decimal at the end. 2,000, never, always, some decimal sometimes, right? Decimal significant, NADS. So there's no leading zeros. There's no in-between zeros. So the decimal implies that the ending zeros are significant, okay? NADS. So this has 4 significant figures. Back to the problem. Número 39, number 39. A solution has a mass of 2,000 point grams and contains 0.050 grams of dissolved solute. What is the concentration in parts per million of this solution? 5.0 parts per million, 25 parts per million, 50 parts per million, or 100 parts per million? Okay, so I don't know how you feel about your own personal arithmetic skills, but if I'm going to divide by a 5, something involving only a 5, with something involving only a 2, there's no way to end up with a 5 in the answer as the final answer. So my actual just arithmetic skills tell me that even if I don't know how to calculate parts per million, that 5 is going to get destroyed by a division by 2. Okay, so that can't be the answer. That can't be the answer. So just arithmetic intuition confirmed that these 2 answers are incorrect. If you don't have that kind of arithmetic intuition, that's great. So what is parts per million? Equals parts per million. Parts per million. Okay? Parts per million. So it's the total number of the solute divided by the total number of millions of solution. So in other words, so this is equal to the part over whole times, if you're doing a percent, remember that percent means 100. Sorry, let me repeat that. Remember, if you're doing a percent, cent means 100. So percent literally means part per 100. That's literally what a percent is. Parts per million is parts, the parts out of a million. So this, instead of multiplying by 100 for a percent, I would multiply by a million. Part over whole times a million. So I get 0.050 grams divided by the 2,000 grams times 1 million. And at this point, I mean, at this point, I'm using a calculator, although I personally don't need it, because there are arithmetic methods that allow me to do this on paper. But I see if I'm going to end up dividing a 5-ish by something involving a 5 with something involving a 2, I got to get a 25-ish or 2.5-ish or a 2 and a 5 somewhere with the decimal moving around. That leaves one answer. So my arithmetic skills actually are making number 2 look very, very nice. But 0.050 divided by 2,000 times 1 million. Now I have to count my zeros carefully, because in another problem, they might have just changed the answers. It might have been like 25, 250, and 2.5. And now you got to count your zeros carefully. 1, 2, 3, 4, 5, 6. That's a million. 25 parts per million. Número 40, number 40. A person with a body temperature of 37 degrees Celsius holds a cup of hot water in their hand. And here's a cup. Okay. The temperature of the cup is 44 degrees Celsius. The air temperature is 22 degrees Celsius. Which phrase describes a heat transfer that occurs in the system? From the air to the cup, from the hand to the cup, from the air to the hand, from the cup to the hand. Heat transfer. Remember what we said about heat transfer in an earlier problem. And this is really a very important thing to know. When you have your air conditioner on, it's summer for me, as you see when the date pops up, I have my air conditioner on. The air conditioner does not transfer coolness. Actually, that's not how air conditioners work at all. The way the air conditioners work is that they make a physical reaction happen with some coolant, which causes the coolant on the outside to heat up. Yes, I did say that. The coolant outside heats up. The coolant heats up. Then the air conditioner releases that heat outside your window, to the outside world out there. And then that cooled down, which the physical reaction which caused the coolant to heat up, now is cooled down. So lost energy comes in, and now another physical reaction causes the coolant to cool down. Remember, it already lost energy. Now it loses more energy, more heat by cooling down, and then it blows air on that cooled interior air on that cooled coolant, and so then the air in the room, the AC takes the hot air in the room and transfers energy from the hot air in the room onto the cold coolant, and then gives us the air back. So the AC doesn't transmit coolness, it transmits heat from our air inside to the coolant in the AC before giving us the air back. And that's how ACs work. Energy, so heat, so energy transfer in the direction from hot to strictly cold, in that order. So let's see. From the air to the cup. From the air is 22. It's 22 degrees. Transferring energy to the cup, which is 44 degrees. No. From the air to the cup? No. It goes the other way around, from the cup to the air. Yes, the air gets hot when you're holding a hot cup of coffee. How about from the hand to the cup? Now the hand is 37 degrees. to the cup, 44 degrees. Cold to hot, that's not how it happens. From the air to the hand, well, the air is 22 degrees Celsius to the hand, which is 37 degrees Celsius. Cold to hot, again, no. And now, from the cup to the hand. Not surprisingly, it was the hot thing to the cold thing. The hottest thing to one of the colder things. That's not surprising to me that that's the way they made the problem. So 44 degrees Celsius to the hand, which is 37 degrees Celsius. That's definitely correct. From hot to cold. Energy heat transfer from hot to cold. Always from hot to cold. You do not transfer from cold to hot. Número 41, number 41. What is the amount of energy or the amount of heat absorbed to completely melt 26.2 grams of H2O at 0 degrees Celsius? Is 8.75 times 10 to the third joules, or is 3.66 times 10 to the fourth joules, or 5.92 times 10 to the fourth joules, or 2.48 times 10 to the fifth joules? Now, this is not the reference table, okay? So we do need a formula. So by the way, this is a phase change diagram, okay? I wanted to add this to you. I wanted to add this to the test so that you could see as you add heat, starting from a solid, like if you put an ice cube in a pot of water, the ice cube doesn't melt, clearly. The solid ice cube gets hotter and hotter and hotter, right until it gets to the melting point, and then suddenly you see the ice cube starting to melt. Like it literally, you'll see the ice cube not melting at all, and then suddenly it just starts to melt real fast, and then all of it melts, and then you see nothing happening because the water is now getting hotter until it reaches this boiling point, at which point you start seeing the water really vigorously boiling. Now, usually we don't have a container big enough to contain that water. So let's say we did have a container that was tight and tight but expandable, maybe covered with a balloon so that it didn't release any water, but kept the pressure the same. Then the water would become a vapor, and then the heat would continue heating the vapor really hot, a lot hotter. So as the phase is changing, the temperature doesn't change. But if the phase is staying the same, then the temperature does change. But let's see. If we go to table 12, table T on page 12, let's see. We have these heat equations. Okay. I'm going to zoom in a little bit to get a higher resolution. So we have these equations here. And specifically, we're melting 26.2 grams of H2O at 0 degrees Celsius. This is the heat of fusion, and which is, freezing. It's also the heat of melting. And then there's this equation, energy is equal to the mass times HF. So there's our equation in table T. Q equals mHF. So what is this number? This is M. And this is melting. We need the HF. And this heat, the amount of heat is Q. Okay? Okay? So we get some numbers here. Well, we know the number M, 26.2 grams times HF. We actually need that number. You might have that number memorized, which is great. Good for you. I mean, the more you have in your mind, the better it is for you as a scientist. But and I do have that number in my mind. It's just one of those weird numbers that I have. 334 for the heat of fusion and 2260 for the heat of vaporization, joules per gram. So 334 joules per gram is equal to Q. And now I have to literally multiply these. And I get something, you know, less than uh, 1,000. So again, 26.2. My less than 1,000 was just me making an estimate for intuition purposes. I do recommend making estimates. 8750.8, which is 8.75 joules, which is equal to 8.7508 times 10 to the third joules. But now I got to go to the right significant figures. This is three significant figures, right? All the decimal, all the numbers are non-zero. So it's got three non-zero significant figures, and there aren't any zeros to stick nads to. And then this 334, it's also got three significant figures, and it's got no zero to stick nads to. So the answer has three significant figures. So 8.7, the 5 would be the third significant figure. The 0 causes the 5 to stay the same. So 5 times 10 to the third joules. And on that note, número 42, number 42. The graph below shows a compound being cooled, beginning in the liquid phase, and we see a temperature going down from 90 to 50, then staying still, then going down again. Let's reduce the size of this a little bit. Which statement describes the average kinetic energy and the potential energy between minute 2 and minute 6? Minute 2 and minute 6. The average, and this is looks like a 2x2 problem again. Does the average kinetic energy and potential energy both decrease, or the average kinetic energy and potential energy both remain constant, or the average kinetic energy remains constant but the potential energy increases, or the average kinetic energy remains constant and the potential energy decreases? Now there's one that I can very quickly eliminate. Choice 3, you remember this is being cooled, so energy is being taken away. For choice 3, the average kinetic energy remains constant and the potential energy increases. That would be an increase of energy. If energy is being taken away, the potential energy wouldn't be the total energy wouldn't be increasing. But this one remains the same, and potential energy increases. That'd be an increase in energy, not a decrease. Okay, so it's either choice 1, both average kinetic energy and potential energy both decrease, or they both remain constant, or the average kinetic energy remains constant while the potential energy decreases. Now, another one that I would eliminate, maybe fake student me is not totally sure about number 2, but it feels weird to say that they both stay constant. Both the kinetic and potential energy remain constant while it's being cooled. Energy is being pulled from this compound. Energy is being pulled from this compound, but then the average kinetic energy and potential energy staying constant. How could you pull energy but keep those two energies constant? That's not physically possible. That makes me think that one's wrong. Fake student me is just not willing to fully cross it out, but real teacher me, I can definitely cross that one out. One of the energies has to go down. So at least. So now the choice 1, the average kinetic energy and potential energy both decrease, or the average kinetic energy remains constant while the potential energy decreases. Now they both have the potential energy decreasing. So now I have that in my head, that the potential energy is decreasing. What about this average kinetic energy? Does the average kinetic energy decrease at between minute 2 and minute 6? We are only in this realm here, minute 2 to minute 6. Only that realm? Or does the average kinetic energy decrease, or does the average kinetic energy remain the same? And this is where I have to remember temperature is equal to a measure of the average kinetic energy. Temperature is equal to a measure of the average kinetic energy. Delta T is equal to, well, it's 50, and at the end of minute 6, and it's 50. 50 degrees Celsius at the beginning. So 50 degrees Celsius minus 50 degrees Celsius is equal to 0 degrees Celsius. So the average kinetic energy stays the same. It might be a little bit counterintuitive, but that actually is what happens. The kinetic energy is staying the same. So how could it stay the same while the potential energy, where is the potential energy going? So first off, it's being lost to the outside world. The outside world in a refrigerator, for example, the outside world is just cold. So the outside world has plenty of energy that it would love to absorb. The sample, being that it's being actively cooled, necessarily has more kinetic energy, more heat than average kinetic energy than the outside world. So the sample is giving its energy away to the outside world. So if it's giving it away, from where is it giving it away? Okay, so for something to go from liquid to solid, it has to lose a freedom of motion, a degree of freedom. That's where that energy goes. So if a substance is able to move freely, literally, like if I'm a liquid molecule and I'm able to move freely, it means that I have a certain amount of energy. If I can move freely, I just do move freely. I'm literally a molecule with a whole lot of energy, right? I'm moving around, I'm moving on a little bit to the side, moving this way, a little bit this way. Now, how can I stop moving? Well, if I stop moving, that means maybe I got locked in. I lost the ability to move, so I lost energy. Remember, as I was moving, I had kinetic energy because I was moving. I had additional kinetic energy because I was moving. Then I lost that kinetic energy, and now I'm standing still, part of a solid. That's where the kinetic energy went. It was lost. Okay? So, número 43, number 43. Which formula represents a saturated hydrocarbon? A saturated hydrocarbon. The first one, this looks like a C2H6, or the second one, C2H4Cl2, or the third one, C2H4, or the fourth one, C2H6O. Okay, so okay, so this one, there's a few things that you need to know in order to be able to do this one. First off, you have to know what a hydrocarbon is. Okay, so a hydrocarbon is made of only hydrogen and carbon. Okay, and that's it. That's it. That's it. Hydrogen and carbon. That's it. So as a result, choice 3 is eliminated because it has chlorine. Choice 4 is eliminated because it has an oxygen. So now we have a passing problem. We have a 50-50 chance of getting it right. And now you have to decide based on your own personal intuition which one is saturated. Now, in my intuition, saturated means filled to the brim. My clothing is saturated with rain. My clothing is literally as absolutely wet as possible. If a meeting is saturated with people, it has just entirely the maximum number of people it can have. Or a sponge is saturated. A sponge cannot carry any more water. Or a napkin, there was a spill of coffee and it's saturated with coffee, it can't carry any more coffee. Saturated means the maximum amount that it can carry is achieved. So which one of these looks saturated? I'm sticking, like fake student me would be sticking to, based on the word saturated, I'm sticking to number 1 more than number 2. And why might number 1 be the correct one? Well, actually, though, let's actually define it. Now let's go from fake student me to real student you and real tutor me. Saturated means the maximum number of hydrogen atoms are reacted with the carbon. With the carbons. And here, if you took one of these two bonds and just broke it. So you got a C, an H, and an H. A C, and an H, and an H. Now you see that both of these carbons, now remember we took a bond and we broke it. Now you see that these carbons both have 3 bonds on the outside, and you know that carbons can totally have 4 bonds outside. So how do you get the 4th bond? You could literally just give it another hydrogen from somewhere and give it this one another hydrogen from somewhere, and you literally have choice 1. So now you've saturated it. So choice 1 is the correct answer. And now you know also how to identify a hydrocarbon that is not saturated. A hydrocarbon that is not saturated has additional bonds between the carbons. Número 44, number 44. Given an equation representing a reaction, this which C2H6 plus Br2 reacts to form C2H5Br plus HBr. Which type of organic reaction is represented by this equation? Addition, polymerization, fermentation, or substitution? Okay, so here we do have to know what kind of reactions these are, and it's important to know each of these. Fermentation, especially if you're like in a biology class, but an addition reaction, okay, an addition reaction, I want to make sure I word this right, is that 2 or more molecules or chemicals combine. Now you might say, well, the H and the Br combine, but actually the H and the Br do combine, but the way it's being done is that an H is being taken from the C2H6, and that's combining with one of the Brs, and while the other Br is going to the place where the H was. So that's not what's happening. Like a great example of addition is like 2 H2 plus O2 form 2H2O. That is an addition reaction. Okay? Or hydrogen plus chlorine forms HCl. So that is an addition reaction. Okay, polymerization is what happens when monomers react to form longer polymers. So that's not what's happening here. The length of nothing is changing. So that's not happening. And then fermentation. Fermentation, this is an important one to know if you're doing biology or if you, care about reactions created by living things. Fermentation is for example, yeast converts sugar into alcohol. That's the classic fermentation reaction. Yeast converts sugar into alcohol. Notice the intermediary, the living yeast, converting the sugar into alcohol. That's not happening here at all. So it's got to be a substitution. And so what is a substitution? Well, 2 atoms or molecules are exchanged. And so if you notice that H and a Br, and this H and this Br kind of get switched. So there's an exchange. That is a substitution reaction. Okay, so it is number 44. And on that note, we go to number 45, number 45. In which compound does sulfur have an oxidation state of +4? Is it K2S or CaS or SO2 or SO3? Sulfur have an oxidation state of +4. Even if I struggled with this answer, there's one answer that I'm going to eliminate. The SO3 how would I react one sulfur with 3 oxygens somehow and get an oxidation state of 3, of 4 rather. The multiples are just not quite right. So what about SO2? SO2 bonds like this. So this has an oxidation state of +4 because the oxygen takes in a electron -2, 2 electrons -2, and this oxygen takes in an electron, 2 electrons, so that's -2. For the charge to be balanced, the sulfur had to get an oxidation state of +4. So that one's looking good. But let's just make sure K2S. I know that K2 is a group 1 metal. Potassium is a group 1 metal. Here it is right there, which means that its oxidation state, it's an alkali metal. Its oxidation state is +1. So +1 +1 and -2. So this has an oxidation state of -2. Sulfur has an oxidation state of -2. And calcium is an alkaline earth metal. It gets an oxidation state of +2. So the sulfur gets an oxidation state of -2, which again, -2 is not. So the answer is and by the way, I would have normally also eliminated choice 2 because now you're talking about a calcium somehow releasing 4 electrons while sulfur gains 4 electrons. That's a lot of electrons to gain. In my head, that's really it. Why I would have, like, the fake student me would have eliminated choice 2. Again, test taking strategies is a big one. Número 46, number 46. Which solution is the best conductor of electricity? So all of 0.0010 molar CaCl2 aqueous, or 0.010 molar, or 0.10 molar, or 1.0 molar. All of these are CaCl2 aqueous. So best conductor of electricity. It's important to know that water is an insulator. And that isn't a thing that many of our chemistry teachers have said to us. But sometimes we didn't buy it because, I don't know, we didn't believe them. But water is an insulator. Pure water, distilled water, hyper distilled water, put 2 electrodes in it and try to conduct electricity. Nothing happens. I had a teacher one day like take water out of a sink or out of a bottle and do the experiment to prove that water wasn't an insulator. Didn't actually realize that the water that he had specifically was an electrolyte water, and the water did conduct electricity. So that was a fun little fail of an experiment. Then he did the same thing with tap water coming out of the faucet, and it was enough of a non-electrolyte that it was an insulator. And distilled water is actually an insulator. Not nearly any ions, really very few ions to conduct any amount of water. So why do I say that? The added ions increase conduction. Therefore, the greater number of salts implies that it has a greater conduction. Which means that, and by the way, just in terms of my intuition, I would have eliminated choice 2 and choice 3 because it has to be one of the extremes just from test taking strategies. If I didn't know that water is an insulator, perhaps choice 1 would have been plausible. But now that I know that water is an insulator, more salts make it more conducting. So it has to be choice 4, 1 molar CaCl2. And on that note, we've already done 46 problems correct towards a perfect grade. So we are 39 problems away from a perfect grade on this Chemistry Regents. And if you're sticking with me through all the way through this point, I'm really proud of you. Let's keep going. Número 47, number 47. Given the incomplete equation representing a neutralization reaction SrOH2 plus 2HNO3 reacts to make some X plus 2H2O, what is the formula of the missing product X? Is it SRO, SRO2, or SRNO22, or SRNO32? And perhaps balancing equations is a difficult thing for you. I know that sometimes it's a difficult thing for me too, so I don't blame you. But what I do look for is what I can say about the reactants and the products. And what I can say to help me at least eliminate some answers, I see some SR, I see some O's, I see some H's, I see some more H's, an N, some N's, and because of the two, and so some N's and some O's again to make some X, and then two H2O's, which has H's and O's. Where are the N's in the reactants? Well, they're not in the H2O, which means that X has some nitrogen, which eliminates choice 1 and choice 2. Even if I'm not sure how to do this problem, I've turned it into a passing problem. 50-50 chance of getting it right. And by the way, I did before. 24 over 4 is equal to 6. Well, 24 over 3 is equal to 8. And look, 24 over 2 is equal to 12. That's a big deal. And if I could do anything to eliminate one of the answers or increase intuition in some way, I can actually increase my score further. So I notice that on the left side, I have one SR, one S lowercase r, plus OH2, so plus 2O, plus 2H, plus 2HNO3, so plus another 2H, plus 2 N's, plus 6O. This is equal to, now I'm going to simplify this. So 1 SR plus how many O's? 2 O's and another 6 O's is 8 O's. Okay? Plus how many H's? 1, 2, and 2 more is 4 H's. Plus how many nitrogens? 2 N's. 2 N's. That's got to react to make the same number of H's, SR's, O's, and N's. So X plus 2H2O plus 4 H's, 2 H's, 2 times H2 is 4 H's, plus another 2 O's. Okay? Now, I do a little subtraction. This means that X has how many SR's? Well, 1 SR. And then how many O's? I have 8 O's on the left. And I have 2 O's on the right, so I need 6 more O's. How many H's? I had 4 H's on the left. And I have 4 H's on the right, so 0 H's. And I have 2 N's on the left and no N's on the right, so I need 2 more N's. So I have SR, parentheses. Now they also give me a gift that I have a 2 here, and they both have an N. So 2 N. So I got my 2 N's. And then I have an O, so that's the same. And now the only difference is if it's a 2 or a 3. And I need 6 O's. To get 6 O's, well, 3 times 2 is 6. So it's got to be choice 4 and not choice 3. Choice 4 and not choice 3. I did it by law of conservation of elements. Yeah, because these are chemical reactions. The number of atoms of each type on the left and the reactants is equal to the number of atoms of each type in the product. Okay. Número 48, number 48. Given the equation representing a reversible reaction, NH3AQ plus H2O liquid reacts to form NH4 plus aqueous plus OH minus aqueous. The water molecule acts as an acid because it accepts a hydrogen ion, or it accepts a hydroxide ion, or it donates a hydrogen ion, or it donates a hydroxide ion. So we said that Arrhenius bases increase the concentration of OH. Arrhenius acids increase the concentration of H's. So acids donate an H plus. Now, how do I know that it's not that the hydrogen accepts a hydrogen ion? This would imply you'd have an H3O plus. Now, accepting a hydroxide ion, you would have somehow H2OOH. That's not something I've ever seen in chemistry class. OH minuses tend to float freely, whereas the H plus, although we treat it as floating freely, it usually reacts with the water so quickly that you do have H3O plus, but you really don't have H2OOHs. So that's not it. Donates a hydrogen ion. That's actually what acids do. It donated a hydrogen ion to the NH3. So got an H plus there, plus OH minus. So it donated that hydrogen ion. That's looking good. But it didn't donate a hydrogen hydroxide ion. What was left of the water, what was left of the water molecule was a hydroxide ion. So it donated a hydrogen ion. Número 49, number 49. Which nuclear equation represents beta decay? Let's see. So I'm not going to read all of these numbers. Well, yes, I am, because I guess some of you might be visually impaired. Got 8137 rubidium plus 1 electron reacts to form 8136 krypton, or 134 beryllium, or we should actually say, let me read the first one again. Rubidium 81 plus 1 electron forms krypton 81, or beryllium 13 reacts to form beryllium 12 plus 1 neutron, or nitrogen 14 plus 1 neutron react to make carbon 14 plus 1 hydrogen 1, or carbon 14 reacts to form nitrogen 14 plus 1 electron. Okay, so I would invite you to think about what beta decay means before you choose before you answer this question, and definitely before letting me answer it for you. Let me just check real quick, because I didn't mark it to see if beta decay was in this one. I was looking at the physics regents, and so like I'm looking at all the regents right now simultaneously. So now I'm mixing the two. I don't want to quote myself as something being true about this table when in fact it's not. I just wanted to see if beta decay is here. They do have a beta minus. That's a beta decay, and then alpha is alpha decay. Okay, but I don't see. There we go. So it is here, table O. The way it's presented in a chemistry in a physics regents is a little different than this, because what you really care about in a physics regents is the name of the particles. But in this case, we have a beta particle right here on table O. So we know a beta particle is here, or an electron. And then they said decay. So the reason I wanted you to pause and give an answer on your own is to analyze what you think decay implies. Uh, there's there's two of these that just don't represent decay. The first one is absorbing an electron. This is not decay. It's not a breaking down of a nucleus. And the second one is also not decay. In fact, I'm not even I'm not even 100% sure in what situations that reaction 3 would even occur. We're talking about like the nucleus of nitrogen releasing an electron. No, absorbing an electron from the neutron. So the neutron releases an electron that somehow is absorbed by the nitrogen to make carbon 14 plus a hydrogen. I don't think that's even a thing. I mean, someone who knows really advanced physics, let me know if that's even a thing. But either way, this is not decay. This is not a single nucleus breaking down into two. The only ones that are single nuclei breaking down into two are 2 and 4. So it's one of these two. So which one of these is the beta decay? Well, it's the only one that releases an electron. This is beta decay. What about the second one? Well, according to this, it's a release of a neutron. Call it neutron decay. So it's not any of these. So even if I didn't know how to do this problem, choice 1 and choice 3 could be eliminated by just knowing that I'm talking about decay. Choice then 2 could be eliminated by knowing what a beta particle is, that it's an electron. And not knowing what an electron is, that could be escaped by going to table O and realizing that a beta particle is an electron and a neutron is not that. Okay? Oops, I just crossed out 4 when the answer is the only remaining choice 4. Número 50, rounding a nice multiple of 10 over here. Given the equations A and B, equation A, hydrogen 2 plus hydrogen 3 react to form helium 4 plus a neutron. In equation B, uranium 235 plus a neutron react to form, of course, choice 3 is a possibility. In a star. Sorry, equation. Let me start off again. But again, I did say post if you know about it. But if you do know about choice 3 and 49, do post about it. Educate the rest of us. Again, chemistry. So I want to focus on chemistry. Número 50, number 50. Given the equations A and B, equation A, hydrogen 2 plus hydrogen 3 form helium 4 plus a neutron. And equation B, uranium 235 plus a neutron react to form strontium 90 plus xenon 143 plus 3 neutrons. Which type of nuclear reactions do these represent? Both A and B are fission. Both A and B are fusion. A is fission and B is fusion, or A is fusion and B is fission. So I do remember from the previous conversation, hopefully you remember, try to pause because we did have a conversation about it earlier, but real teacher me and also real tutor me and also fake student me do remember that fission reactions occur in nuclear reactors with like uranium and plutonium. Uranium and plutonium are fizzed, broken into pieces, and the energy released by that is fission. Is a fission is huge, but it's also a fission reaction. So this is definitely fission. So this is a 2x2 question. It's a 2x2 question because it's asking, is A fission or fusion? And is B fission or fusion? B is definitely fission. So choice 2 is crossed out. Choice 3 is crossed out for sure. Now I might struggle with knowing whether A is fusion or fission and B and whether whether A is fusion or fission. Choice 1 says A is fission. Choice 4 says A is fusion. Now, again, fusion is the combining of lighter elements to make heavier elements. So you have a lighter hydrogen react to form heavier helium. Okay. That's the wording that I've always used, but now I'm realizing maybe the wording is not quite right because, of course, helium-3. No, I'm sorry. I was about to misspeak. No, that is good wording. Later hydrogen, H2, hydrogen-2 and helium and hydrogen-3 react to form helium-4. So that is actually accurate. So this is fusion. And fusion is a reaction that takes lighter elements, nuclei of lighter elements, and reacts the nuclei to form heavier elements. So A is fusion and not fission. A is fusion, B is fission. Okay? And I want you, if you want a general thing to remember, lighter elements fuse, heavier elements fizz. Lighter elements fuse to make the heavier elements. The heavier elements fizz to make lighter elements. And you might wonder, where did the heavier elements come from if they had to fizz, if they only fizz? Well, the answer to that is the only way to make something that literally is the opposite of what would normally happen is to add so much energy to it that that reverse reaction can actually occur with enough frequency that you get a sample that appears in nature. I think that it's really cool to know that that does happen. If you've ever been engaged and gave your partner a gold ring, that gold ring was made in the last seconds to milliseconds of a dying and exploding star. So in order to, and I think that's a beautiful thing, that you're gifting your partner something that required millennia, eons of time and reactions in the order of in orders of magnitude that go beyond the amount of energy that a whole universe produces in just a fraction of a second. And all of that energy went into a product that you're giving a partner when you're asking for their hand in marriage. Or, just getting a nice watch for fun. Número 51 and 52. Base your answer to 51 and 52 on the information below and your knowledge of chemistry. That's a cool green flame over here. Now, part B2, by the way, part B2, literally a lot like part the number 1 through 50, except that multiple choice questions are completely gone. Completely gone. Okay? So, let's see. The reading. Compounds that contain the element boron, such as boric acid and sodium borate, produce a green flame when a sample of one of these compounds is placed in a laboratory burner flame. If this flame is viewed through a spectroscope, a bright line spectrum is seen. State how the bright line spectra of known elements can be used to identify an unknown element whose bright line spectrum was viewed through the spectroscope. Again, bright line spectra of known elements used to identify an unknown element. Well, so basically what's going on is almost like a dictionary. When you do a bright line spectrum of this, you're going to see a bunch of colors, probably something in the green, right? And definitely a bunch of colors that in our eyes add up to approximately green. When you see boron being burnt, okay? So, what if I had a chemical and you didn't know what it was, but then you look at the burn and it kind of looks like this. It kind of looks like this, but maybe you're colorblind like me. And I am colorblind. I actually am colorblind, along with 9% of males and about 1% of women. What if you're colorblind and you can't really see the green? And when I say I can't see the green, I mean that looks kind of yellow. I know it's green because I'm actually mild proton. I can actually kind of see the green, but it turns out that when you look at the bright line spectrum, you actually see bright lines, and it actually you look at the list, and it's almost like a dictionary, but instead of words, you literally have just lines at different colors, vertical lines at different colors, including in the case of boron, green. So maybe I burned something. I don't even know what it is, but it looks green. And I'm like, I think there's boron in it. Let me look at the bright line spectrum. And I look at the bright line spectrum, and then I look at the bright line spectrum in a dictionary for boron, and I see that they're identical. And then I say, this chemical has boron. So that's exactly what it is. Um, the bright lines can be compared to the spectra of known elements because the spectra of each element, this is kind of the important thing, is unique. Meaning you see the bright line spectrum of boron, you see the bright line spectrum of hydrogen, you see the bright line spectrum of oxygen, the bright line spectrum of even argon, the noble gases. The bright line spectra are unique. It's like a fingerprint, except that a fingerprint is like 99 something percent accurate, point something percent accurate, whereas the bright line spectrum of these chemicals is basically 100% accurate. When I say basically 100% accurate, I mean there might be a ton of bright line spectra and you kind of have to tease things out, but once you tease things out, 100%. Kind of like a DNA test. Yeah, they say, oh, 99.99 something stupid percent. DNA tests are basically 100% accurate. The only loss of accuracy in DNA tests ends up being human stupidity. Um, let's call it human error. Sure. Número 52. State in terms of electrons in shells why the electron configuration 221 is an excited state of a configuration of a boron atom. Boron is has 5 electrons. So boron um, looks like this. Has in energy level 1, it has 2 electrons. And then in energy level 2, it has 3. Okay? Energy level 2. So to get into an excited state, I'm going to put this one in like this weird color. I don't like it because it's actually a little bit too similar to the blue to me. Hey, colorblind, yay, if you're colorblind. Let's go for the red, except red is also a not colorblind friendly color. I might have to choose my colors a little bit better. Knowing that I'm colorblind, how can I choose? I might have to think about it. Let me think about it. But you might take one of these electrons, hop it over to over here. But to do that, you have to give the electron energy. Okay? So you could say here the electron configuration of boron is 2, 3. So the configuration 2, 2, 1 requires energy to move an electron to level 3. Okay? There's a lot of different ways that you can word that. You don't have to word it exactly the way I did, but that's basically what they want you to know. You could just anything that just tells them that you know that energy is required to move the electron from level 2 to level 3 is going to give you full credit. In fact, that what I just said is a great answer. Energy is required to move the electron from level 2 to level 3. If you literally just wrote that, that would be a perfect grade for that one. And we're 52 questions in, 33 questions away from a perfect grade on this Regents. This is 53 through 55. Silicon is an element in group 14 on the periodic table. The atomic mass and natural abundance for the 3 naturally occurring isotopes of silicon are shown in the table below. Naturally occurring isotopes of silicon, isotope notation, Si 28, 29, and 30. Atomic mass, U, 27.98, 28.98, and 29.97. And natural abundance, 92.22%, 4.69%, 3.09%. I read the table, but I just let that sit and let it process however my brain processes tables while I move on with the reading. Literally, subconscious processing, not participating in the processing of that table while I go to number 53, number 53. Draw a Lewis electron dot diagram for an atom of silicon in the ground state. Okay, turns out I didn't really fully need the table because I can go to the reference table and look up silicon, okay, in the ground state. Yes, it is helpful to know these by heart, okay? Silicon is in group 14. Conveniently, by the way, for the group 14 elements, the preferred oxidation states, or the number of, or I should say actually the number of valence electrons is equal to the number after the 1. So group 1 and 2, 1 and 2 valence electron, and group 13 through 18, 3 through 8 valence electrons. And as we know, actually group 3 also has 3 valence electrons, but so do every element from 3 through 13. Okay? So 1 and 2 each have 1 and 2 valence electrons. 3 through 13 have 3 valence electrons. 14 has 4 valence, 15 has 5 valence, 16 has 6 valence, 17 has 17 valence, and 18 has 8 valence electrons. Okay, so now I look at silicon again. Silicon is in group 14, which means that it has 4 valence electrons. Okay, so it says draw a Lewis electron dot diagram for an atom of silicon in the ground state. Turns out that they actually accept 2 answers for this, and I do appreciate that. Here's the answer that I prefer. It's Si. I put a dot up here. 4 valence electrons. You got to put 4 dots around the silicon. This 1, 2, 3, and 4. That's the one that I prefer. Although, for very good reasons, Si, they also accept this one, where you put 2 here, and then the 3rd and the 4th go just separate. I think I like this one because I think of the way pure silicon can construct itself as in different crystalline structures, and somehow that's the way my brain works. But the second one, the red one, actually makes a lot more sense in terms of orbitals. The s orbital of silicon, the 2s orbital of silicon is filled. Did I say 2s? Nope. The 3s orbital of silicon is filled first before 2 of the 3p orbitals each get an electron. That's why the red is chemically more accurate. And if you notice, silicon can either take in 4 electrons, or it can release 2 electrons, or it can actually release 4 electrons. There is no releasing 3 electrons. Número 54, number 54. Compare the energy of an electron in the first shell of a silicon atom to the energy of an electron in the third shell of the same atom. So this is the thing that you need to know. You need to know. So electrons in lower energy levels have less potential energy. Electrons in lower energy levels have less potential energy. This is the thing you need to know. Okay? So this one says to compare the energy of an electron in the first shell of an atom to the energy level in the electron in the third shell. And you could say the electrons in the first shell, right? First shell, lower energy level, have less potential energy than electrons in the third shell. That's a point. Número 55, number 55, show a numerical setup for calculating the atomic mass of the element silicon. The atomic mass, remember now, the atomic mass is a function of the abundance of isotopes of silicon on Earth. On Earth. And so we have to take into account the percentages. And so how do we do this? Well, we take into account the percentages. So we get the 27.98. Well, how do you take into account the natural abundance, 92.22%? You could do times 92.22 over 100. So in other words, that's the amount of, so that's the mass of silicon 28, and times this is the abundance of silicon 28. And then you do the same thing for silicon 29 and 30. Plus the atomic mass of silicon 29 is 28.98, but the abundance on Earth is 4.69 over 100, 4.69%. So again, this is the, I'll write this in black, this is the atomic mass of silicon 29, and now this one is the abundance of silicon 29. And then you do the same thing for silicon 30. So plus, and I won't describe it in writing, but it's the same thing. The atomic mass of silicon 30, 29.97, times the abundance, 3.09 over 100. Atomic mass of silicon 30 times the abundance of silicon. And that's the answer. They did not want you to give the number. They just want you to show a numerical setup. Okay. Next, base your answer to question 56 to 58 on the information below and your knowledge of chemistry. The unbalanced equation below shows a reaction between nitrogen monoxide gas and oxygen gas to produce nitrogen dioxide gas. Number 56, state in terms of reactants and products why this reaction is a synthesis reaction. A synthesis reaction. We talked about an addition reaction, and synthesis reaction, right? Why is this a synthesis reaction? And so you're taking two compounds and merging them into a single compound. So you could say that two reactants merge to form a single product. Done. Full credit. And by the way, I have this picture here. This is what NO2 looks like. And this is what N2O4 looks like. Notice that NO2 and N2O4 have the same empirical formula, NO2, right? Which means that these chemicals should actually be, these two chemicals should actually be in equilibrium with each other, since they both can exist. Now, If you change the temperature between in a sample of NO2 or N2O4, it actually can transition between mostly NO2 to mostly N2O4. So that's why like one of them is darker and one of them is lighter. Okay, and if you're wondering, this one on the left is the colder one, and this one on the right is the warmer one. Okay. Número 57, number 57. Balance the equation in your answer booklet for the reaction using the smallest whole number coefficients. So how do I first I'm going to actually balance it on this paper and then bring it over to the answer sheet. Here's the answer sheet right here. So I have NO gas plus O2 gas forms NO2 gas. So I see that the left side and the right side have the same number of nitrogens, and they both appear once. So the NO and the NO2 have to have the same coefficient. Right now, if they both have a 1, which they do, how can I get the O2 to react in a balanced amount to get NO2? Well, I can't increase the amount of O2 because that gives me more oxygens. I only have 2 oxygens on the right. I'm already starting with 3 oxygens on the left. So if I increase the amount of oxygen, then I'm on balance. So I'm going to try doing this, putting a 2 here and a 2 here. And if that doesn't work, I could do a 3 and a 3, 4 and a 4, 5 and a 5 until it works. So if I put a 2 in front of the NO and a 2 in front of the O2, I notice now I have 2 nitrogens on the left and 2 nitrogens on the right. On the left, I have 2 oxygens from the NO and 2 more oxygen from the single O2. That's 4 oxygens. And on the right side, I have 2 times 2 is 4 O2. That's 4 oxygens. So I have 4 oxygens on the left, 4 oxygens on the right. This is balanced. 2, 1, 2. Okay. Número 58, number 58. Determine the percent composition by mass of oxygen in the product NO2. The percent composition by mass of oxygen in the product NO2. The gram formula mass is 46 grams per mole. Okay? So that's one significant figure. I'm sorry, 2 significant figures, 46. So I'm going to use the mass of O2 as being two significant figures as well. And I noticed that I'm looking for the mass of oxygen. So I've seen students get this wrong by getting the mass of the nitrogen. Well, tough. I mean, but the point is that the lesson here is that they're not tricking you by asking for the oxygen. They could ask you for in this problem, they could ask you for the nitrogen. They can ask you for the percent composition of mass by oxygen. They could ask you for the percent composition of by mass of nitrogen. They can ask you for the mass of oxygen. They can ask you for the mass of nitrogen in a known sample. They can ask for the number of moles of atoms in a known sample. Lots of different questions. So in this case, they're asking the percent composition by mass. Well, I know I'm going to get something bigger than 2/3 since I have 2/3 of the atoms are oxygen, and oxygens are heavier than nitrogen, or more massive than nitrogen. So the mass of O2 is equal to 16. So the percent composition by mass of oxygen, I have 16 plus 16, it's 2 oxygens. Or a better way to maybe say it is 2 times 16. Divided by the total mass is 46, which is equal to 32 over, and I have to do it by times 100 because it's a percent composition. So 32 over 46 times 100. And now I have to go to my calculator. 32 over 46 times 100. And I get 69.56 percent. So now I'll tell you what I recommend to my math students. I recommend putting all the digits in the calculator now. Okay. Oops, that's interesting. Okay, putting all the digits in the calculator now. So equals 69.5621,739%, which is equal to, and then round. So these are all 2 significant digits. So the first 2 digits are significant. And so the 5 tells me to round up. I get 70.5. Great question here. The 70%, if you put the point there, is that going to be full credit? Or if you don't put the point, do you lose a point? Let's actually find out. So I want to point out here that the rating guide says here in big letters for teachers only. That does not mean that you can never look at it. This is literally freely available online. The only reason this is for teachers only is so that teachers don't accidentally, when they're giving out the test, they don't accidentally also print out the answers and give them to you. All right, so let's go for number 58. Let's look for the valid answers here. 70 point percent, or any value from 69.55% to 70% inclusive, 70 point percent inclusive. And I notice here that they are not even dealing with significant figures. After all, they're allowing 69.55%, which is 4 significant figures, which leads me to think that perhaps they would accept 70% without a decimal. And they said any value between these two, and 70% is between those two inclusive. So that they would accept it without the significant figures, which is nice. Base your answers to 59 and 60 on the information below and your knowledge of chemistry. The ionic radii of 4 group 17 elements are given in the table below. Ionic radii of 4 group 17 elements, and I just quickly look: ion, F minus, Cl minus, Br minus, I minus. Ionic radius, PM, picometers, 133, 181, 196, 220. I let that absorb how it does. Número 59, identify the noble gas that has atoms in the ground state with the same electron configuration as Br minus in the ground state. Now, Br minus, I have to then look where bromine is. And if I remember my elements, I think the element after bromine is krypton. So I think krypton is looking good to me. Okay. Br minus has 35 protons, right? And so Br minus has 1 extra electron. 35 plus 1 is 36. And the element that has 36 electrons is krypton. So Br 35, so 35 plus 1 is equal to 36. So the answer is krypton, because krypton has 36 electrons. You don't have to give the reason. You just have to identify the noble gas, by the way. So if you just said krypton, you're done. So I'm giving you this as the reason. Maybe I should put that in red so that you know that this is the reason. Okay, state in terms of electrons why the ionic radius of group 17 elements is larger than the atomic radius of the same element. The ionic radius of group 17, so literally taking group 17, adding an electron to it, that ionic radius is larger than the atomic radius for the same element, for krypton. So literally, like bromine minus, Br minus is literally physically bigger than krypton. Well, why would that be? What's the only change that happens between bromine, Br minus, and krypton? The electron configurations are identical. The only thing that changed is the nucleus. The only thing that changes is the nucleus, and the nucleus of krypton has 1 more proton. So that's what's happening. So we have 1 more proton, which means a higher positive charge in the nucleus. So you could say the extra proton in krypton attracts the 36 electrons more strongly. Okay, and other valid answers, I wrote that the extra electron in the ion is shielded from the positive charge of the nucleus by the other electrons. And I also wrote that the net electric charge of the atom is 0. So the electron in the ion is orbiting. The electron in the ion is orbiting a particle with charge 0. They would have accepted any of those answers, but here it is. The extra proton in krypton attracts the 36 electrons more strongly. We have 60 problems. We're literally 60 problems into getting a perfect grade on this chemistry Regents. We are 25 problems away from getting a perfect grade on this chemistry Regents. We are going gung-ho. We are pushing, and if you're up to this point, I'm really proud of you for continuing to push, and let's keep at it, because our goal is to get the grade that we want on this Regents. If your goal is to just pass, and I get it, but if you write down what I write down, you will get a higher grade on this Regents. So literally, I do recommend writing down everything that I write down, and you will do better. It's better than just listening. Even if you're one of those students who are listening to this at like 2 speed, because the Regents is in about an hour, writing what I write down is actually going to help you. It's going to help it enter in 2 different ways: seeing it, hearing it, and writing it, as opposed to just seeing it and hearing it, which could be too passive. By writing it, it actually makes the seeing and hearing more active, and it adds a third layer, the writing, so you learn through 3 different modalities. So, and that's if you're trying to just barely pass, write everything I say down. If you know you're going to pass, but you're trying to get that 80, write everything I said down. If you're trying to get that 90, write everything I said down. And if you're just like at a 98, but you're trying to get that 100, write everything I said down, and you will get a higher grade. Okay. Base your answer to 61 and 62 on the information below and on your knowledge of chemistry. The diagram below represents 2 sealed, rigid containers and the conditions of pressure and volume and temperature for each container. Container A is filled with N2G gas, and container B is filled with O2 gas. So I quickly read the table. Container A, N2 gas, and I do semi-process it, but I let my subconscious process it, all right? So container A, N2 gas, P equals 101.3 kPa, V equals 750, T equals 298 Kelvin. O2 gas, P equals 101.3. I notice that they're the same. I let my brain process that how it does. V equals 750 ml, same volume. I let my brain process it. 298 K for the temperature. Again, same pressure, volume, and temperature. I let my brain process that how it does. Okay? Subconsciously. And then I go back to the table and do thinking. So, número 61. Explain in terms of the strength of intermolecular forces why the gas in container B at standard pressure has a higher boiling point than the gas in container A at standard pressure. So the gas in container B has a higher boiling point. Now I have to explain that in terms of intermolecular forces. And we already did a problem about intermolecular forces. And if we learn something from it, you might be able to answer this question a little bit more strongly. Now, but it was this one, and we didn't do the problem with these same gases, these same liquids/gases. But what we did learn in that conversation is that the chemicals with higher intermolecular forces would stay liquid for higher temperatures, and the chemicals with the lower intermolecular forces would turn into gas fast at lower temperatures. So now they're saying that the one on the container A, the nitrogen, has a lower boiling point, and the gas in container B has a higher boiling point at standard pressure. Okay? And remember, the pressure is not changing. The volume, we assume, would have to stay the same to not have too many variables. So it has to be in terms of intermolecular forces. Higher boiling point implies higher intermolecular forces. And so then my answer is going to be exactly that. So the container B, the molecules in container B have higher intermolecular forces. So my answer is this: the gas in container B, the gas molecules rather, in container B have a higher intermolecular force. Finito. Finished. Número 62, number 62. In the space in your answer booklet, show a numerical setup for calculating the pressure if the gas in container B is cooled to standard temperature. A numerical setup for calculating the pressure if the gas in container B is cooled to standard temperature. Now, standard temperature is 273. You do need to know that standard temperature is 273 Kelvin. Okay? So how can we possibly do this? Luckily, there is an equation. We don't always have an equation for every single thing that we need to do, but there is a combined gas law in the reference tables. Okay. So I have P1 V1 over T1. The equation I have is P1 V1 over T1 is equal to P2 V2 over T2. And now they just said a numerical setup. They don't actually want you to calculate it. So to start, pressure 1 was 101.3 kPa. V1 was 750 ml. Over T1 is 298 Kelvin, if I remember it right. Yep. P1 V1 over T1. Okay. And now the numerical setup calculating the pressure if the gas in container B, remember, rigid container, is cooled to a standard temperature. So the container size isn't changing. So I got the 101. Now the pressure, we're looking for a pressure. The pressure is a variable. Okay. So P2, unknown, but the volume is still 750 milliliters. And now the standard temperature is 273 Kelvin. And that's my answer. Okay. Not bad. And we don't have to solve it, which is nice. If we did have to solve it, I might use some intuition to do some simplification. I noticed that the 750 cancels. This temperature 2 is a little lower, so a little bit lower, so the pressure 2 is going to be a little bit lower too, just to make a quick estimate. That's a full credit problem. Base your answer to questions 63 to 65 on the information below and your knowledge of chemistry. The table below shows the formulas of 3 organic compounds and a chemical name for 2 of the compounds. Compound 1, propyl butanoate. Compound 2, blank. Compound 3, 2-propanol. Número 53. Identify the element in these 3 compounds that allows them to be classified as organic compounds. So this is a definition. This is a definitional statement. Organic compounds contain carbon. So the compound that allows them to be classified as organic compounds, carbon. Okay. So identify the class of organic compound to which compound 1 belongs. This is propyl butanoate. Well, I mean, if you know this, great. It's not a multiple choice question, but And if you know it, congratulations, you've been studying really hard, which is great. And by the way, do I think studying the reference tables is a worthwhile use of your time? 100%. Let's see, propyl butanoate. Propyl butanoate. I see in the last line a methyl propanoate, and now on the third to last line, and now I look over here, I have a propyl that's CCC with H7, and then a COO, and then sorry, I misspoke, a CCCC on the left with H7, and on the right I have a CCC with an H7, and then I have the COO in the middle. So if I go to my reference table, I have this R. So again, R is a functional group, and X represents any halogen. R is a functional group. So R, COO, C double O on top and single O on the right, and then another functional group. That is exactly the format that that chemical takes on. That's the chemical one takes on. Okay, so except that this is a propyl butanoate. So here for problem 1 for 64, R is equal to CH3, CH2, another CH2, and then R prime. So you got C, a double O on top, and O on the right, and then it's on the right. R prime is equal to CH2, CH2, CH3. Propyl, R prime, butanoate, the CH3, CH3, 2, CH2, and then the COO. Okay, so this is, and what category is this in? It's an ester. The class, it said the class of organic compounds, class of compounds. So we look in the header, it says class of compounds, functional group, general formula, example. Okay, so this is an ester. Okay, and then the third one, watch this. Write a chemical formula for compound 2. Chemical formula for compound 2. So you see CH2, CH2, COOH. A chemical name, sorry. I didn't say, I said chemical formula, but it says 65, write a chemical name for compound 2. And if you notice CH2, CH, and the CH3, CH2, COOH, CH3, CH2CO, I missed the O. So it's clearly, I like, it didn't match my notes, and I'm like, hey, what just happened there? So clearly that kind of mistake, if I can do it, you could do it too. CH3, CH2, COOH, no, CH3, CH2, COOH, and that is here exactly this one. So propanoic acid. Okay. Surprisingly, they didn't make it that tough. They could have put in like a butanoic acid or ethanoic acid or methanoic acid, but they chose to use the one that's exactly on the reference table, which is a very, I mean, you might not call it a kind thing, but it is a kind thing to me. And that's 65 questions. We are 20 questions away from a perfect grade on this Regents. Base your answers to questions 66 through 69 on the information below in your knowledge of chemistry. The periodic table of elements has changed over the past 150 years. And remember I said that the element names are going to be given right now. During this time, many elements have been added as they were discovered. The elements 113, 115, 117, and 118 in period 7 were named in 2016, and the other ones were also named more recently. Their official names have been approved by the International Union of Pure and Applied Chemistry, IUPAC. The table below lists the names, symbols, and atomic numbers for these 4 elements. Recently named elements in period 7, element name, nihonium, muscovium, tennessine, and oganesson. Atomic number of 113, 115, 117, 118. Element symbol prior to 2016, UUT, UUP, UUS, or UU and UUO. U stands for un. U stands for un again. T stands for tri. So unontridium. Unontridium means 113 trium. UUP, pent ium. UUS, septium. Literally 117 tium. O, act ium. 118 ium. Ununatium. But now their new names are nihonium, moscovium, tennessine, and oganesson. Okay? All right. Número 66, number 66. Identify the element in this table that is located on the periodic table of elements in the group classified as a noble gas. Noble gas. So that would be the very last column, as we know. The noble gases are in the very last column. And that would be UUO, 118, oganesson. Okay. Because here, oganesson, group 18. Okay. Now, the fact that 118 ends in an 18, that's just coincidence. That just happens to be true for all the elements from 104 to 118. Just a coincidence. That coincidence doesn't happen on other lines. Okay. Number 67, number 67, they explain in terms of valence electrons why the elements nihonium and tennessine would be expected to differ in their chemical properties. Why oganesson and tennessine might differ in their own chemical properties. Tennessine to oganesson, or oganesson to tennessine, why they differ from each other. Okay, so notice that oganesson is group 18 in the noble gas list, and tennessine 117 is in the halogen column, group 17. So tennessine would be expected to have 7 valence electrons, and oganesson would be expected to have 18 valence electrons, 8 valence electrons. So 7 valence and 8 valence. So they have different number of valence electrons. And valence electrons participate in chemical reactions. So there's an explanation why oganesson and tennessine might have different chemical properties. Número 68, number 68, describe the general trend in the first ionization energy values as the 5 elements above moscovium in group 115 on the periodic table of elements are considered in order of increasing atomic number. So let's just be clear. They said the elements above moscovium in group 15. So we are looking at the column group 15. Group 15. Okay? So it does, as you know, it's extremely helpful to know this, but it happens to be that we can look it up during the Regents. So we want to know the first ionization energy trend. And in this case, let's remember the elements are group 15. Okay. So nitrogen, phosphorus. So now we can go to the reference table and look at the first ionization energies. Nitrogen, whoa, sorry about that. Fast scrolling. Nitrogen, first ionization energy, 1402 kilojoules per mole. 1402. Phosphorus, 1012 kilojoules per mole. Arsenic, 944 kilojoules per mole. Antimony, SB, 831. And now I'm seeing a trend here for first ionization energy. And bismuth, 703 kilojoules per mole. So what's the general trend? As you move down the periodic table, what's going on with these numbers? 1402 down to 1012, down to 944, down to 831, down to 703. As you move down to the periodic table, to increase, that's an increasing order of increasing atomic number. As you move down the periodic table, the first ionization energy decreases. Okay. So, number 69, number 69. State in terms of protons why tennessine is listed before oganesson in period 7 on the periodic table of elements. So this is the thing you've got to know. I mean, why are things, and hopefully you've noticed this, that they're all listed by atomic number, right? And atomic number is defined by the number of protons, right? So you do kind of need to know that. Literally, when the person first figured out how to organize these, they literally figured out that you could organize them by number of protons, and that immediately led to the hypothesis that there were some missing elements that they hadn't discovered yet, because like just some proton numbers were just missing. Yeah, so the reason literally tennessine, which is 117, is to the left of oganesson, 118, is that it has one less proton. Okay, so tennessine has 117 protons, and oganesson has 118 protons. Okay, elements are listed in order of how many protons they contain. And that's a perfect grade right there on that problem. Base your answers to questions 70 through 73 on the information below and on your knowledge of chemistry. Hydrogen gas is needed for many industrial chemical reactions. As an equilibrium system that includes the use of a catalyst produces hydrogen from methane and steam is shown in the table in the equation 1 below. Equation 1, CH4 gas plus H2O gas plus 210 kilojoules, double arrow means reversible reaction, CO gas plus 3H2 gas. Another equilibrium system produces hydrogen gas as represented in equation 2 below. CO gas plus H2O gas, double arrow mean reversible reaction, CO2 gas plus H2 gas plus more energy, plus energy. So the first one took in energy, the second one released energy. Número 70, number 70. Compare the rate of the forward reaction to the rate of the reverse reaction for the equilibrium system at equilibrium represented by equation 1. So here's the thing. Well, it said in equilibrium. So in equilibrium, the everything, the number of reactants is equal to the number of products. So literally the rate of the forward reaction is identically equal to the rate of the reverse reaction. And that's exactly it. So again, in equilibrium, one, naively might think that nothing is happening in equilibrium, but in fact, it's the opposite. There's tons of reactions happening. It's just that the forward reaction rate and the reverse reaction rate are the same. The rate of forward reaction equals the rate of the reverse reaction. That's a definition in equilibrium. It's a definition. So that's a definition. So what's the answer to this question? Compared to the rate of the forward reaction to the rate of the reverse reaction. So the rate of the forward reaction equals the rate of the reverse reaction. Done. Okay. Número 71. State how the equilibrium shifts when the temperature of the equilibrium system at equilibrium represented by equation 1 is increased. Now, this one's an interesting one. This one does require a little bit of knowledge of chemistry. Because what changes when you increase the temperature? You might, I mean, your first intuition might be that nothing changes, but let's say something does change. What changes? So equation 1 requires energy on the left side for the right side to happen. So the left side compounds plus energy produces the right side compounds. The left side compounds plus energy produces the right side compounds. So if that extra energy is needed to make that reaction occur. If that energy is freely available, well, then that forward reaction can actually increase in rate. Vice versa, if not much energy is available at all around in the area, then the reverse reaction is less likely to occur. So what do we, and in this problem, they're actually increasing the temperature. So that increase in temperature gives the chemicals an initial boost of energy. So you only need a little extra energy beyond that to make the forward reaction occur, which means that some of the 210 kilojoules can come from just the kinetic energy that the average molecules have, which means that the reaction on the left increases, producing more reactants on the right. So that's what happens. So, and just in general, that's what we could say. As you increase the temperature, the rate of the side that requires energy increases, so that the amount of the products ends up increasing after that reaction occurs. So the rate of the left side increases until the new equilibrium is found, and then the quantity of the right side is increased. So that's what we need to address. So some activation energy is provided by the thermal energy. So I should say not just some, more activation energy is provided by the thermal energy, by the increased thermal energy. So the rate of the forward reaction increases until a new equilibrium is met. Okay? Número 72, number 72. State in terms of activation energy why the catalyst increases the rate of the forward reaction in equation 1. So this is again in equation 1. So what does a catalyst do? So this does take a little bit of knowledge again of chemistry. So what does a catalyst do? So a definition, a catalyst, what does a catalyst do to begin with? Okay. Increases the rate of a certain reaction, okay? In one direction, in some direction, okay? Maybe the forward reaction, maybe the reverse reaction, but how does it do it? So by reducing the activation energy. So if you ever wonder, wait, how does a catalyst actually work? It just somehow sits there, doesn't get used up, and then magically the reaction just speeds up like crazy? Yeah, but that's how it does it. It actually reduces the activation energy. And the way it does it, it changes the reaction so that the reaction may take multiple steps. Like the reactants react in some way with the catalyst. The catalyst somehow participates. And then that new chemical that is created with the catalyst then reacts with everything else to form the same exact products as we started with. The catalyst is not used up, but it happens to be that extra in all those extra steps, the activation energy for any of those steps is lower than the activation energy of the original reaction. So state in terms of activation energy why the catalyst increases the rate of the forward reaction in equation 1. And equation 1, again, there's a big energy right there. So that activation energy is reduced. So the catalyst reduces the activation energy. So the rate of the forward reaction increases. Okay. Número 73, number 73. On the labeled axes in your answer booklet right here, draw a potential energy diagram for the forward reaction represented in equation 2. Now let's go back to equation 2. We see the forward reaction. This is a potential energy diagram. The forward reaction reacted to form two other chemicals, but there's more energy released on the right. So the energy was released in this reaction, which if energy was released in this chemical reaction, then that means that the potential energy in this reaction went down. So that is how we start. So we start flat, and we should try to start as flat as possible. We don't need to draw a straight edge, but we should start as flat as possible. But then now the activated complex is formed, and the activated complex always has more potential energy. So the reaction always does this peak, okay? Every single reaction will start at some level and will always go up to a peak. Now, this is for your own edification. What will happen after this? One of two things will happen. The reaction will either do this, flat, and then flatten out, or the reaction will do this and flatten out. It'll drop. It'll still drop and flatten out, but the question is, will it drop above the original level, or will it drop above the original level, or will it drop below the original level? And now this one, it released energy in this reaction 2 released energy in the reaction, released potential energy in the reaction, and therefore the potential energy goes down below the starting point. So we're going to drop from this peak below the original starting point, before flattening out. And that is a full credit graph. You don't need straight edges. You don't need your curves to be perfect. This is a great graph. Okay. So but just for edification again, we started with the two chemicals. They collided in just the right way to form an activated complex with a potential energy that's higher than the original reactants. The activated complex was formed and then they broke up into the final products, and the final products have a potential energy that's lower than the previous ones because than the previous reactants because energy was released. All right. Número 74 to 77, 74 to 77. Base your answers to 74 to 77 on the information below and your knowledge of chemistry. The diagram and the balanced ionic equation below represent an operating voltaic cell, a battery. Okay. So you have a couple of liquid fats. 1.0 molar FeNO32 aqueous with an iron electrode with a wire connected to a voltmeter going across with another wire connected to a copper electrode, which is in a bath of 1 molar CuNO32. Okay. And I see there's a salt bridge, a liquid salt bridge. It's got liquid in it. Okay. And on the bottom, they have this reaction, Fe solid plus Cu2 plus aqueous reacts to form Fe2 plus aqueous plus copper solid. Okay. Then number 74 says, number 74 says, state the form of energy that is converted to electrical energy during the operation of this voltaic cell. Well, this is all chemical reactions. We are dealing with chemical energy. So this is definitely a chemical energy that is converted chemical energy. Ooh, what just happened there? That was interesting. Chemical energy. It's a chemical energy. During the operation of the voltaic cell. Chemical energy. Okay. So number 75, and you could say chemical energy, you could say chemical potential energy, either one of those correct. Numero 75, number 75, identify one metal from table J that is more easily oxidized than copper and less easily oxidized than iron. So we got to go to table J. Okay, so more easily oxidized. And it does say in the table, very important thing, it does say in the table, right on the bottom, H2 is not a metal in the tiniest letters. Okay. So I gotta minimize this a little bit. I know this is gonna be a little bit blurry on your screens, but I gotta minimize it a little bit so it fits on the screen. More easily oxidized than copper. Here's the copper. Less easily oxidized than iron. And then I'm going to repeat that it says here H2 is not a metal. So H2, hydrogen 2 is not a metal. So more easily, so if we look at most active down to least active, more easily oxidized than copper, which would mean going higher up, not H2 because it doesn't count as a metal. So we have Pb, lead, Sn, tin, Ni, nickel, Co, cobalt. Okay, any of those answers would have been valid. And so if you literally have to choose any of those and you get your point. So, and you could get the letter, you could give the name. So CO, you give the name, or you could have, written like nickel. or given SN or PB or lead or tin, okay? So any of these answers would have been valid, okay? But I chose CO for my answer. Okay, number 76, state the purpose of the salt bridge in completing the circuit in the cell. All right, state the purpose of the salt bridge. So one of the things I used to wonder before learning this in chemistry, where do the electrons come from and where do the electrons go? After all, I know that conservation of mass has to be satisfied, but also the law of conservation of charge has to be satisfied. So you can't just pump a bunch of electrons through a circuit and like the electrons just gather, right? They don't appear because, and not for nothing, electrons have an immense amount of force associated with each individual one. It doesn't take many electrons to like push a large, that's a macroscopic object that you could see. You could literally measure on an oil droplet, the Millikan oil drop experiment, you could measure the charge effect of a single extra electron or a single missing electron in an oil droplet. Um, so where do the electrons go? So the electrons cross the voltmeter, but then they react with the with one of the metals. They react with, let's see, the iron loses electrons, the copper gains electrons, right? Iron goes from iron 0 to iron +2. That's a loss of electrons. And copper +2 goes from missing 2 electrons. That's a charge of +2, meaning I'm missing 2 electrons, to copper solid. So the copper gains 2 electrons and solidifies. But then charge has to be conserved. And charge is conserved because the iron also loses 2 electrons. But the thing is that the charge can't gather on one side because that's not physically possible. So the ions have to be able to cross from one side to the other, and that's how they cross. They cross over the salt bridge. And so that's actually the purpose of this salt bridge. The salt bridge literally allows ions to flow from one cell to the other. So that's actually what happens. Electrons flow through the wire, and the ions flow through the salt bridge. So the salt bridge allows ions to flow between the cells. Okay. Between the cell. Cell, singular. Okay. Número 77, number 77, write a balanced equation for the half reaction that occurs in the copper half cell. So again, the copper half cell, the copper is gathering more and more and more copper. So the copper is solidifying, but from what form? It used to be an ionic, an ion floating in the liquid, in the water. And then it gains 2 electrons and attaches to the copper solid. So what happens here? Copper +2 ion, AQ, plus 2 electrons react to form copper solid. That's the half reaction. Sweet. And we learned a lot about how wet cells work. Base your answers. This is our second to last big problem. We are literally almost done. We're in the high 70s out of 85 problems. We are stoked. I'm stoked. Base your answers to questions 78 to 81 on the information below and on your knowledge of chemistry. In a laboratory investigation, a 0.010 molar NaOH AQ solution with a pH value of 12 is used to determine the molarity of an HCl aqueous solution A 10.0 milliliter sample of the HClAQ is exactly neutralized by 20.0 milliliters of the 0.010 molar NaOH-AQ. Okay. During the laboratory activity, appropriate safety equipment is used and safety procedures are followed. State the color of the indicator litmus in a sample of the original NaOH solution. Now I added a picture of the litmus, but I guess I didn't. I guess it deleted while I've been working. But I want you to remember this: that the litmus paper turns blue. Blue. Is this blue or is it blue? Okay. In a basic solution. Your basic blue. So it turns blue in a basic solution. Okay? Basic blue. Turns blue in a basic solution. Litmus paper turns blue in a basic solution. Número 79, number 79. Determine the pH value of a solution that has a hydronium ion, that's H3O plus, concentration 100 times greater than the original NaOH aqueous solution. So this one actually does require you to know how pH is calculated. Let's just look in the formula sheet. I just want to check to see if the formula sheet actually has pH formula. It does not have a pH formula, and I don't recall it being anywhere else. I don't know. Let's see if it mentions pH anywhere else. And I know I'm scrolling really fast. It's weird because I noticed that when people scroll, they scroll a lot faster than we would scroll, and it's harder to follow somebody else's scroll. So I apologize. My scrolling, I know you might not be able to follow it, but I just was checking if they have a calculation for pH in the sheet anywhere, and they don't. And so you do need to know that pH is measured logarithmically. Okay, logarithmically with a base of 10. Okay, so log of 100, that's 100 times greater concentration of hydronium ions. Now the hydronium ions, this is H3O plus. Log of 100, log base 10 of 100. Now I know college kids might be complaining that I put log of 100 to mean log base 10 of 100, but in the US, high schools, log is log base 10. And I know that when you get to college and in many sciences, log ends up being log base E, and that does cause some transition confusion, especially if internationally you're using log as log base of E. This is log base 10, so log of 100 is equal to 2. Okay? So I could actually write that here. Actually, so log of 100 is equal to log of 100 is equal to 2. And then also, so this is a pH decreasing ion, because hydronium ions is what's produced when acids are put into the concentration. So this is going to reduce the pH by 2. 12 minus 2 is equal to 10. And so that's the answer to number 79. Numero 80, number 80, identify the positive ion in the original HClAQ solution. Again, the positive ion in the HCl solution, they actually allowed the hydronium ion. So H3O plus. But, well, no, it's not, we shouldn't be shocked if they allowed it. That's the ion. What I mean is that, well, and also that it's a little bit of a gift because if you happen to know that that's a hydronium ion, that kind of just told you that. Um, but the other thing is that they actually also allowed the H plus ion. I gave this ion because I had a feeling like they might not accept the H plus ion, but they did actually end up accepting it. So, but H3O plus is the answer I gave. Okay, and number 81, numero 81, determine the molarity of HClAQ solution used in the titration data. Now, just intuitively speaking, the amount of NaOH needed to neutralize the HCl is double. So that means that the molarity of the H plus would then be double the molarity of the NaOH, which means I should be getting 0.020. Okay? Let me see if there's a calculation. There's not a titration calculation. Okay. So molarity. So we have molarity is equal to the number of moles divided by the number of liters. Okay? Molarity is equal to the number of moles. There we go. So that is in the formula sheet. So this formula is in the formula sheet. So let's put that. So the molarity of let's see. So if we go back to the problem, let's read it a little bit. So the molarity of the NaOH is 0.1010 molar. Okay. So we need to know the number of moles. So we know, so that means that 0.010 molar is equal to the number of moles. I'm going to say M moles divided by the number of liters. It was 20 milliliters. 20 milliliters was needed according to the problem. So 20 milliliters is 0.02 liters. So if I multiply both sides by 0.2 liters, okay? And so then that's equal to 0.010 times 0.02. And this is a very small number. This is equal to the M is equal to 2, that's 2e to the fourth of 0.0002 moles. Okay? So if that's the number of moles that I needed for the NaOH, remember that NaOH is a strong base and HCl is a strong acid. So this is the number of moles of NaOH. And this therefore is equal to the number of moles of HCl. Okay? How do I know they're the same again? Because the NaOH is a strong base, HCl is a strong acid. So the entirety of the OH ions from the NaOH reacts with the entirety of the H3O plus ions or H plus ions from the HCl. So they have the same number of moles. So now I use the same formula to find the HCl molarity. Okay? Now the molarity is equal to the number of moles, again, divided by the number of liters. And now the molarity is 0.0002 moles. Now it's equal to the number of moles. I'm sorry, wrong. The molarity, I'm going to use for capital M. I'm going to say capital M. Now is equal to the number of moles is 0.0002 moles divided by the number of liters. We have to go back to the problem to find how many liters of HCl is 10 milliliters. So 0.01 liters, which is equal to. Now I gave you a verbal argument and they would have accepted that verbal argument. And that's okay, but getting the easy argument from me and getting the points on the regents are different things, and you're taking the regents, right? So that's why I couldn't just give you the explanation and called it quits there. Not for you, if I wanted you to get the best grade possible. It's 0.02 molars. Molar. And they would have accepted 0.02 molar, 0.020 molar, whatever you said. So I got that answer. I'll put the 0.020 just to have the right number of sig figs. Because that should have had an O from the beginning. Okay, but what I had said before would have been a valid answer. You could have said, like I said, that twice. So you could have said that the acid and base are strong bases. You could have said that the volume of NaOH aqueous solution that was needed was double the volume of HCl needed. Therefore, the molarity of the HCl is double the molarity of the NaOH. But that wouldn't help you on the regents. This does help you on the regents, this calculation. So, number 82 to 85. And listen, I'm not going to ask you to subscribe again. I'm going to say it one more time. I think if I've earned your subscription, and I think that if you watched it this far, that I have earned your subscription, you are an absolute powerhouse for making it through this point. And I'm telling you, I believe in your ability to do just phenomenally well on this Regents. And I'm proud of you for having made it all the way through to this point. My best advice to you at this point, if you've been taking notes, you're going to do great on this test. If you haven't been taking notes, I recommend going back through the video and starting to take notes, especially on the problems that you didn't get right or you didn't know how to do. And if you need a method, again, to go through a video a second time to get as much out of it, listen and read and also write down everything I do. And if your Regents is in an hour, do watch this at double speed. Or if the Regents is in like 3 hours, watch this, or the Regents is tomorrow, go ahead and watch this at double speed and write down everything I write down. And you will get a phenomenal grade tomorrow. But that said, this is the last time that I'm going to speak about it. I'm literally going to finish number 82 through 85 and end the video right there. But I'm proud of you for having made it this far. I really am. If you feel that I've earned a subscription, do please hit the subscribe button. I am trying to get to 1,000 subscribers so that all of those ads that YouTube puts on this video, instead of the ad revenue going to YouTube solely, a certain percentage of it goes to me, and that allows me to fund the process of making these free videos. All right. So base your answers to question 82 to 85 on the information below and on your knowledge of chemistry. Spacecraft sometimes use a nuclear power source that produces electricity from the heat released by the beta decay of radioisotopes. Two radioisotopes that have been used in these nuclear power sources are plutonium-238 and americium-241. Okay? Both the plutonium-238 and the americium-241 emit alpha radiation and gamma radiation. The half-life of americium-241 is 432.7 years, Other sources of electrical energy for some spacecraft have been solar panels and batteries. Okay? Determine the fraction of americium-241 remaining from an original sample after 865.4 years. We have not had spacecraft for that long, have we? It's interesting to think that in those spacecraft, they're going to have americium-241 for a very long time. I noticed, so we have to calculate how many half-lives passed. So we have to do the original mass. Divided by the new mass. And that's equal to that's equal to 860. I have to pause for a second. That's equal to 865.4 years divided by 432.7 years. And that's equal to just the number 2, 0.000. And so what is this? This is the number of half-lives that have passed. Okay? So now we know the number of half-lives. Now there is a formula. Let's check if there's a formula on the formula sheet. This is the last set of problems, so not every formula is going to be on the formula sheet. Let's see. Temperature, heat, no, titration, combined gas law, concentration, percent composition, percent error, mole calculation, density. So this formula is not on the formula sheet, which is interesting because like the physics test is such a formula heavy test. Literally every formula is on the formula sheet, all of them. Sometimes people think that physics is easier because of that. The fraction of sample remaining is equal to 0.5 or 1/2 to the power of the number of half-lives. So how much of the original sample it remains is 0.5 to the power of number of half-lives is 2, and you need a calculator for this. A lot of students think, oh, half of the sample disappears after the first half-life, and then the second half, all of it's gone. That's actually very false, and that's a very, very, very false assumption that a lot of students make. Because the thing is that no matter how much you start with, half the sample is gone after a half-life. No matter how much you start with. So after one half-life, you have a certain amount. Give another half-life, half of whatever remained at that point is left. So 0.5 to the power of 2 is equal to 0.25, 0.25. So that's the fraction of the sample remaining, okay? And it says, and that's the answer to the question, okay? Numero 83, number 83. Compare the penetrating power of the alpha particles to the penetrating power of gamma radiation. Now, this is an important thing to know. And I don't, again, this is a thing that I don't see on the reference table. And I did look. I looked all over the place. I don't see anything about penetrating power. And I'm sorry for scrolling. If it's making you, if it's hard for you to look for a scrolling, please do look away at least temporarily. And but the point is, I looked for penetrating power, and I don't see anything. That is a physical reaction. Nope, no penetrating power. No penetrating power. Yeah. So you do have to know this one. You do have to know this one. If you feel there's a subscribe button as a reminder. Anyway, so how this is what you need to know. Half an alpha particle. An alpha particle is like kind of a bit like a bowling ball. It can come at you with a lot of energy, but a bowling ball hits you with that energy. It's not gonna penetrate. Whereas a gamma ray is small with the same amount of energy or more energy often, but let's say that even the same amount of energy, it's a photon, it can actually penetrate through you real easily. Think X-rays. X-rays penetrate really easily. Gamma particles penetrate really easily. So this is what you need to know. alpha particle has less penetrating power than gamma radiation. Alpha particle has less penetrating power than gamma radiation. You just need to know that. The next one, complete the nuclear equation, 84, número 84, complete the nuclear equation for the alpha decay of plutonium-238 by writing a notation for the missing nuclide. 84, and this is the equation, plutonium-238 with atomic number of 94, arrow, helium 4 slug 2, that's the alpha particle, helium 4 with 2 protons, plus some missing nuclide. Well, the missing nuclide, if plutonium decays by losing 4 nucleons, well, 238 minus 4, according to my calculator, and you're allowed to have a calculator, is 234. So the mass has to be 234, that mass number. And also, the number of protons goes from 94 in plutonium. 2 of those protons are lost to the alpha particle of the helium nucleus. 94 minus 2 is equal to 92, according to your calculator. So 92 is the number of protons, and we can actually just read off on the table which element has 92 protons. Where's the 92? Where is the 92? 89, 90, 91, 92. Here it is. 2 below plutonium is that nice uranium. U. So uranium 234. That is the nuclear equation completed. And numero 84, number 85, we're literally the last question away from a very, very perfect grade on this Regents. And I want to say I'm proud of you for making it this far. I have full confidence in your ability to do phenomenally on this test. You just study real hard. You keep going. You do what you got to do for yourself for that test tomorrow. Like I said, bring the snacks that you need. If you've never drunk coffee, don't bring insane amounts of coffee. Bring decaf coffee. And that caffeine, that tiny amount of caffeine in decaf coffee, which it does have caffeine, will do the same exact thing that to you as regular coffee does to me. So it's worth it. Or don't bring coffee at all, which may be a wiser decision. Número 85, number 85. Compare the energy released by the radioactive decay of 1.0 kilograms of plutonium-238 in this nuclear power source to the energy released by 1 kilogram of chemical reactants in a battery. It doesn't even ask us to calculate it. It just says to compare it. Why do we have nuclear power plants? Think about this. A nuclear power plant with an extremely small amount of plutonium, meaning not extremely small, it could be a few kilograms or a few tens of kilograms, a few hundred kilograms, but that's not replenished. Whereas a power plant with like chemical reactants, you're literally shoveling coal into the power plant just on a repeated basis. You're just burning and burning and burning more and more and more. Clearly, if a power plant literally gets supplied with plutonium like once, and then it runs for an extremely long amount of time, clearly the plutonium power plant has releases a ton more energy, and that's literally what it's asking us to do. Compare the energy released by the decay of 1 kilogram of plutonium to the energy released by 1 kilogram of chemical reactants. So let's write it, and let's get our perfect grade on this Regents right now. The energy released by radioactive decay of 1 kilogram of plutonium, okay, is, I'm going to say orders of magnitude greater than the energy released by 1 kilogram of chemical reactants, period, and mic drop. That's a perfect grade. Good luck.